Welcome to this screencast on functional programming in Java 8. And functional programming is not going to be restricted to Java 8. It's going to be a permanent feature of the language, and we can expect in the future there will be refinements and improvements of what's available in 8. We're looking at the working file courseoverview.txt. We're in my Emacs editor, and I've highlighted in roughly a page the major features. But let me cut to the quick and go to two important points. The first, of course, is requirements. What do we need? And the only thing we need is core Java on a local machine. So this is Java Standard Edition 8 or greater. That's it. And of course, an editor or an IDE to your preference. But everything that I'm going to be showing you will compile straightforwardly with core Java 8. Now, for all of us programmers, the big question is, why these new features in Java? Java is already a general purpose language. It's rich in features. We now have more features. And if you're a programmer, of course, your immediate reaction is, uh-oh, something more to learn. So what is it and why is it so important? So let me hit 2 points to begin, and then we'll move to a very simple depiction. It's clear to all of us that we're working in a big data world. So programs now regularly get rich data sets. Typically, these are streamed in, often, of course, from remote sources, in other words, over the network. And we're also working on multi-core machines, that is, multi-processor machines. And in the Java world, of course, the way you take advantage of multi-processor machines is through multi-threading. So big data and multi-core machines are the environment, you might say, in which it's important to place these functional programming constructs in Java, because they're really targeted at this environment. So let me try to get more particular. What I have down here in roughly the middle of the document is a depiction of what might be called a data pipeline. So there's a rich data source to the left. For example, this might be customer data. And what we want to do is filter that data. We might want to pick out, for instance, the customers that buy the most from us. And after filtering those customers out, we might want to do some processing. For example, do averages, typical statistical measures, and then send the output to yet another filter. We might want to pick off the top 10% or the top 10% that buy a particular product, do further processing, and so on. In the end, we may want to collect these results, in other words, aggregate what we have, and then generate reports, and so on. Once this pipeline is in place, the idea is we don't want to change the structure of the pipeline, but we do want to plug in, for example, different filters, different processing elements, and so forth. And the high-level way to do that is by plugging in different functions in these stages. So, for example, one filter would be implemented by a particular function, another filter by a different function. This is now easy to do in Java 8 because we can simply stick functions in as filters, as processing elements, and so on. So this is the big picture, the environment in which Java 8 functional programming works best. Now, as for the details, what Java 8 gives us basically are two new things. First, and this is the one that's gotten the most attention, so-called anonymous or unnamed functions, Lambdas. That's what everybody calls these for historical reasons. Lisp is the language that really popularized the use of this term. But functional programming also includes method and constructor references, which are equally powerful and easy to use for programmers. So what we're going to be doing in this course is focusing on lambdas, method and constructor references, and the sort of applications in which these make sense. We're going to be looking at lots and lots of code. Like you, I'm a programmer who says, show me the code. Let's see the examples. Let's see how things work concretely. So you can expect to see in my Emacs editor lots of Java code, and I'll jump to the command line in order to compile and run. So we'll do code examples and a thorough analysis. This is going to be a hands-on, code-driven course. This lesson introduces Java's version of the Lambda, where a Lambda is an unnamed, sometimes called an anonymous function. And we're going to see 4 examples of it shortly. First, let me give you the basic syntax. So it's depicted here in this comment. You have an arg list. The arg list is normally parenthesized, and then you have an arrow followed by a body. Now, the arrow is meant to suggest mapping, because in math, of course, a function is something that maps its arguments to a value. That's similar in programming, of course, but functions are a little bit richer in programming than they are in math. For now, I'm going to pass over without comment this binary int op type. It's defined up above. It's an interface type. We will look at it. And I want to instead focus on the 4 examples. So I have an object reference add, another sub, another mul, and another div. They all do pretty much what you'd expect. And these are referring to, on the right-hand sides, 4 different Lambda expressions. The idea behind the examples is we go from the relatively complicated to the quite simple. So each step along the way, I'm going to drop something, in effect. So the first example, I have my 2 arguments, and I've got them explicitly typed. They're both ints. Notice there's no return value shown here. And here I've got the traditional Java brace for the body of a function, return arg1 plus arg2 semicolon. The second example is a bit simpler because now for the body, I've dropped the braces, I've dropped the return, I have a single expression arg1 minus arg2 that is the implicit return value. Now, in general, if you have a very involved body, many statements, you need the braces, but a very involved body is against the spirit of lambdas. So in best practices, the simpler, the better. So this would be very simple and appropriate, so you don't need a return, you don't need braces, you have a single expression. In the third example, the change now is that we've dropped the parens around the body. We don't need them. We have a simple, unambiguous expression. We're just multiplying the 2 args. That's it. And the last one is the sort of example you're going to see the most. In this case, in the argument list, the arguments are not explicitly typed. I don't have ints. The reason is that the compiler can figure this out. We'll show how momentarily. So I just have arg list arrow expression. It doesn't get any simpler than that. Simple, clean. My 2 cents is this is absolutely wonderful. The less clutter, the better, and you don't have any. Now, to test this, I basically invoke each of these Lambda functions using the object references add, sub, mul, and div, and you'll notice in each case I'm calling compute. So let me now jump up and explain where that comes from. So at the very top of this working file, again, this is intro to fp.java, I have an interface defined. I call it binary int op, any name would do, and I annotate it as a functional interface. As we'll see later, you could drop that, but it's nice for readability. There's one restriction. It's in the documentation, but let me emphasize it here. This functional interface must declare a single abstract method. Now, I've put in abstract here for emphasis, but you could actually drop that. Here's the important part. I need to say what the return type is. If there is none, then void, of course. Any name would do. 2 arguments, I give the data types, and then this is the important guy here, the semicolon, not the braces. If you have braces, you're defining a method. We're declaring the method as befits an interface. Now, the compute here is the compute called, let me jump back down to the print statements, is the compute called in each of these 4 examples. So what's happening at the conceptual level, not at the syntax level, is that when I define, for example, divide, and that's up here again, what's happening is binary int op compute is assigned in effect to this Lambda expression. As I said, that's conceptual. We don't care how the compiler works its magic here. What we care about is how do we use these lambdas. So in this case, as you can see, I simply call compute 4 times. That's that abstract method declared up in the interface. But now it's no longer abstract because it's been assigned in effect to a Lambda expression that executes. Now, the proof, of course, is always in the pudding. Let's close the Emacs editor. Let's go to the command line. So I'm ready to compile. And as you can see, it compiles in the absolutely normal way. Now I can simplify this to run it. So I just execute it in the normal way, and I get the output that is shown in the editor. So those are the system out print line statements. So we've had our first look at lambdas. You can see that the syntax is almost ridiculously simple and wonderful in that sense. It's really minimalist. I applaud the Java designers for that. And we've shown how these can be used. What we're now going to do is tweak this example some, and then we'll get into some more advanced examples. This lesson recommends a short programming exercise. We're looking in my Emacs editor at lambdaexercise.txt, and it makes some suggestions about what you might try in the experiment that I'm going to recommend. But to get into the details, let me return to the original example, and that's intro to fp.java. So this code compiles and runs, and the idea is to experiment a bit with it. All of us as programmers from time to time learn new syntax and the like by taking existing code, playing around with it, trying to break it, and so forth. And that's very much the spirit of this exercise. So it shouldn't take long. I think 15 or 20 minutes should be plenty. But the idea is you should learn quite a bit in trying different things. So let me start with the obvious one. The documentation claims here that you can omit functional interface and everything will behave as it should otherwise. So you might comment this out and try that. A more important experiment, and one that's critical to how these interfaces work, is the following. What you might do is to declare another abstract method. Any abstract method would do it all, and then check to see if the program still compiles. Now, in Java 8, you can have within interfaces so-called default methods. These are static methods, and they are defined in the interface. In other words, you would have the braces and the whole thing. So if you have time, you might try adding one of those as well to see if that's okay. So what we're trying to find out in this part of the experiment is basically what are the restrictions for one of these functional interfaces. Now down here in the body, as noted, I provide some examples basically from more complicated down to simpler syntax. But in all of the cases, notice that the argument lists are always in parentheses. So the question is this necessary? You can see on the right-hand side, in the body of each lambda, in one case we have a brace because we have a return statement. So another obvious part of the experiment would be, can you drop the braces and keep the return? We've already seen that you can drop parens around the body if you have a simple expression, as in the third and fourth examples. So the idea is just to tweak the code a little bit, try to recompile it, and see what happens. Now, if you have a bit more time, what you might try is this. These examples of executing the lambdas are very straightforward. So add compute, and basically two variables are passed in as arguments. But one would expect that you could also have nested calls. In other words, the first argument to subtract actually might be this invocation of a lambda right here. In other words, you might have lambdas whose arguments are the return values from other lambdas. So if you have time to push the experiment in that direction, that would be useful as well. In sum, the idea is to tweak this code, see if the tweaks still allow the code to compile, and if you have a bit of time, what you might do is try to do richer examples using the object references provided, add, sub, mult, and div, to build up more complex Lambda expressions. This lesson is a review and assessment of the Lambda exercise. To that end, I've written a second version of that intro program. This one is called Intro to FP-Exer, and we're looking at the source code in my Emacs editor. This file will be included among the working files. I thought what we might do is go over some changes that I've made, and we can talk about what works and what doesn't. To begin, this annotation at functional interface is, as the documentation claims, strictly optional. You can comment it out, you can take it out, it has no impact whatsoever. I like to use it just to remind myself when I come back a bit later that I really am using this interface as a type for a reference that refers to, in this example, a lambda expression. In fact, more than one. We have 4. We have an add, a multiply, a subtract, and a divide. Now let's get to changes that are far more significant. Right down here, I have this commented out, and let me uncomment it now so we get the color coding from Emacs. Let me describe the problem. What we have on this line is abstract int compute, returns an int, takes 2 int arguments. So this is a method declaration, ends with a semicolon, and we're allowed to have exactly 1 in one of these functional interfaces. This second candidate returns Boolean, has nothing to do with addition, subtraction, and so forth, and it takes a single argument of type float, so it's purely made up on the fly. But if you leave this uncommented, the code will no longer compile. Now, the error messages are not the great. These always take some time to refine, and Java will do better, but for sure, you'll get a fatal compilation error message. So I'm going to comment this out yet again. So the rule, once more, is that one of these functional interfaces must declare abstractly exactly 1 method. Now, what's omitted from this are so-called default methods. Default methods are actually defined. I have 2 of them as proof of concept. You can see the braces here say hi, and compute default, you can see the braces here. So the braces contain the method definition. These are both static, and they don't fall under the restriction just mentioned. So I've got 2 of them, and I'm actually going to invoke them from my code. So let's move down then to the demo section. Again, once more as proof of concept, I invoke the default method say hi. I invoke the default method compute default, and these work just as you would expect. Now, this section of the code is unchanged from the original, and down here I make some changes to indicate the results of experimentation. So these 3 examples are absolutely straightforward. As you can see, I'm calling the add, the subtract, and the multiply, and it's clear that each of these does in fact return a value which is stored in an int variable, k, m, and z in this particular case. So this reinforces the idea, if we jump back up here to multiply, that multiply refers to a lambda. It's shown on the right. This particular lambda does not have an explicit return statement. Nonetheless, the value of this expression, arg1 times arg2, is the implicit return value. It's returned, and it's stored down here in Z. So again, I do a quick printout to show that this is possible. Now, one of the things about lambdas is they really are first-class objects in Java now. And so, for example, just as you can nest method calls in Java, so you can nest lambda calls. No difference at all. So I have something here that I call composed. It basically takes 2 arguments, and then as you can see, it's a little more complicated than anything we've seen before. There's an addition. The first argument to the addition involves a subtraction, and then another subtraction, and the second argument involves a multiplication. So these are all composed together, and then I can call this lambda, compose, compute 500 and 100, print out the answer, and I get this rather meaningless number, but it does show as proof of concept that the composition works straightforwardly. So lambdas can be nested to any level. This nesting behaves just as it would were these method calls instead. This lesson also focuses on lambdas, but now we're going to look at a different aspect of lambdas. Up here at the very top in the documentation, I have some explanation about higher order functions. The short version is this: a higher order function is a function that can take another function as an argument. In the case of Java, that other function would be a reference. So you could have a reference to a lambda, you could have a method reference, a constructor reference. We've not yet seen the syntax for method and constructor references, but we're going to get there. Now, as you come down here, I've still got my functional interface from before, binary int op. I've still got a single abstract method declared called compute, but this file is now lambdas as args.java, and it will be included in the working files. Now, higher order functions are very, very useful in data pipelines, and we're moving up to a data pipeline example. In this case, we're going to focus mostly on the syntax. So let me move down to the demo section, and let me now introduce a slight twist on what we've already seen. Java has the runnable interface, that's java.lang.runnable. It's used, of course, in multi-threading within Java, and that interface declares a single abstract method. I show it here, public void run, and because there's a single abstract method in the interface, runnable automatically counts as a functional interface. So I can do this sort of thing as proof of concept. I have an object reference called that, proof of concept. Its data type is runnable, and it refers to a lambda on the right-hand side. This lambda is slightly different from anything we've seen before. No arguments, so I have the empty argument list, and then the body now consists of the familiar system out print line in Java. So this works perfectly fine. So I can do proof of concept dot run. In effect, the lambda on the right becomes the run in runnable. So we've provided, in effect, an implementation for the run method. Now, down here, I've got a very simple example from before. I'm using divide, and it refers to the lambda on the right, arg1, arg2. That's unchanged. And then what I do is call it in the conventional way, conventional being the way we did it before. I use the object reference and I invoke compute, and then I do something a little bit different. I call apply. Apply is a higher order function because its first argument is a reference to a function, in this case a lambda. So in the first call, I actually send the object reference as the first argument, but in the next example, I sent a lambda itself written in place. So you can see argument list x1, x2. I've not given the data types. The compiler will figure that out. Arrow x1 times x2. And then these are the actual arguments I want to use. So let's go down and take a look at apply. So apply is our first look at a higher order function. Here it is. It returns an int. The first argument is of type binary int op, because that's the particular functional interface that we're using. The more particular the information you give to the compiler, the better. So the compiler knows from this that the function that we're going to send as this first argument has to take two ints and return an int. And indeed, the ones that we send up here, the div here, and the, in effect, multiply in the second case, those fit the bill. And then the second two arguments in apply, A1 and A2, in this case, are basically the arguments to what I'm calling this bio for binary int op. So down here, what we do is return object reference, compute as usual, A1, A2. So we've used a function, apply, to call another function, which is the first argument to apply. By the way, in Java, there is no restriction on where functional interfaces can go as argument types. Could be the first, could be the second, could be all of the arguments. In some languages, you have some restrictions. There's also no special syntax involved. Notice you couldn't really tell by eyeballing this line alone that binary int op is actually a function reference. It could be something else. The syntax is clean, it's straightforward, it's exactly what we'd want. So this represents our first look at higher order functions. We're going to be seeing an awful lot of these, so it's good to get this out on the table. In this lesson, we're going to put a Lambda function to practical use. So far, our focus has been on the syntax of lambdas, how lambdas can be referred to, how they can be passed as arguments to functions, and so on. But now we're actually going to use lambdas in a way that is familiar to many Java programmers, in particular Java programmers who work with event handling. We're in my Emacs editor. We're looking at the source file cleanercode.java. That's included among the working files. I've already compiled it, and I'm about to run this application, so let me jump to the command line to do so. So I've compiled and I'm ready to go. And as you can see, it's a very, very simple graphical application. You may have written this sort of thing yourself. And I've got a label at the top. It displays the current time. And if I click the button, the time is updated. So there's an event handler, a piece of code that I've written and that the system executes that basically refreshes the time label. So let me do it one more time. We're at 1811 for minutes and seconds, and we're now at 1826. So I'm now going to close this guy and jump back to the Emacs editor. Now, most of this code is not of particular interest to us. What we want to focus on is the event handling. So let me give you the short version. I have a button. I call it Update Current Time, so it's a J button. And I set the font on it. I basically add it to the window. And now I need to handle click events. So here's the old way of doing so. What I'm going to do is uncomment this for now so that we get the color coding that comes with Emacs. A little easier to read. But this doesn't actually function, so this is the old way, but I could do it this way. So I do update current time, add action listener. Now imagine that you're brand new to Java, you've never seen this sort of thing before, and consider how confusing this is going to be. So we come over here, you see new action listener, and we tell the new user, for example, imagine this is a tutorial, we say, well, action listener is an interface, and supposedly you can't new an interface because an interface by its very nature is abstract. However, the syntax here is a bit misleading. What you're really doing is an unnamed inner class that implements action listener. And in fact, when the code is compiled, there's going to be an additional class file. There's going to be cleanercode.class, of course, but there's also going to be cleanercode$1.class. And that file represents this unnamed inner class in my code. So anyway, we knew what seems to be an interface but really isn't. And now we define action performed. Of course, the override up here is optional. It's there for emphasis. We do the action performed and we set the text of the current time, that's the label, to the new date toString. Now, this is more code than we should have to write. This is a bit clunky. I think even defenders of this way would admit that. And by the way, this represents an improvement over even earlier ways of doing this. But now I'd like to jump down to the use of Lambda to do the same thing, because this is a winner, I think, hands down. So here's update current time again. That's the button. Once again, we invoke add action listener. That's how we register the callback. And now it can't get much simpler than this. We're going to get an event, in particular an action event. So I'm just calling it E. I'm not typing it. Notice, by the way, I don't need to parenthesize the argument because there's only one. So E is the event. The compiler will figure out the appropriate type. Here's the arrow. Here's the body, current time. That's the label, set text, new date toString. This sort of example is often cited as one of the selling points for the new Lambda functions in Java 8, and appropriately so. It's nice and clean, and the thing you want to keep in mind is compare this again against this up here. Certainly, once you've written one in the old style way, you get used to it. You're going to do copy and paste code. It's not that big a deal, but certainly this is terse, it's clear, it's simple, and it gets the job done. In this lesson, we're going to look at a second example that underscores how Lambda functions represent a better way to traditional Java. So we're looking at the source file, cleanercode2.java. It's a sorting application, And before we get into the details and before I illustrate it at the command line, let me just review very quickly so-called qsort semantics, named after the qsort library function that's included basically with every operating system, written in C as old as the hills. I'm not suggesting that this sorting library is being used. It is, however, in many cases, but the comparison function that is used in qsort is basically set the bar for what modern comparison functions do. The comparison function, I've done this roughly in pseudocode here, returns an int and it compares two items. The order of the items is important. So one is the first and the other is the second. And during the sorting routine, the system library, for example, is going to call this compare function as needed. So it's a typical callback. You and I write it, but the runtime invokes it. So the semantics are the following. 0 means that the two items are to be considered equal for purposes of the sort. In other words, there's no need for the sort to change their order in the original list or array. Less than 0, for example, -1 or any negative integer, means that the first item should precede the second in the sorted outcome, and greater than 0 means that the second should precede the first. So the semantics are very simple, but they're also enormously flexible. This basically means you can do ascending sort, descending sort, and you can customize sorts in any way that might be appropriate for you. So it really is very well done from the start, and it's no surprise that everybody has copied it. Now, I'm going to use this in Java in two examples, once again, an old way and a new way. So first, let me jump to the command line to illustrate. So I've already compiled the code. I'm now about to run it. And basically, I do two sorts. And as you can see, under unsorted, we've got roughly arbitrary order. And then the resulting sorts are in descending order in both cases. So I'm just generating some integers, sorting them, and then outputting them. Back to Emacs and back to the code. So let me talk about the setup for the traditional way of doing the sort. There's more than one way in Java. Java is very rich in its variety. And what I'm using in this particular case is the comparator interface. So I'm declaring something called int numC. It's going to be used to compare integers. So you can see that on this line. And then what I need to do is implement the compare function. Again, it follows the qsort pattern. It returns an int, and in my case, I'm going to be comparing integers, but this could be employees or anything else. And what I'm going to do is return n2 minus n1. So basically, if n2, for example, is greater than n1, then what I'm telling the runtime system is that n2 should precede n1. If it's the other way around, then n1 should precede n2. So that gives me the descending sort. So again, the setup is a little bit clunky, a little bit cumbersome. This is not something that a new programmer to Java would pick up immediately. So I need this guy because when I come down to sort, so I populate an array. You can see that up here, an array of 32. I populate it with random numbers. That's of no interest to us right now. I print it out, and now I sort it. So I'm using arrays.sort, and the second argument is this int numC. So the comparison function is basically this guy right here. Now the new way. Once again, populate the array, print out the unsorted version, and now arrays sort. First argument again is the array, and the second argument in place is a very simple lambda. n1, n2. Once again, we let the compiler figure out the data types. No need for us to do that. And then the body consists of n2 minus n1. That gives us the descending sort. If you reverse the order, and you might just play with it to reassure yourself that it is the case, if you reverse it to n1 minus n2, you're going to get the sort in ascending order. So this is nice and clean. So this is yet another example of how lambdas can be used in what might be called everyday Java. simply to clean things up, to give you code that is clearer, easier to understand, easier to maintain, easier to tweak. This lesson is a wrap-up of Lambda basics. We've talked about the syntax of Lambdas, we've seen some practical uses, we've looked at the big picture, the fact that Lambda functions are at the center of the functional programming constructs added in Java 8. So this gives us a chance to go through some details and to review them. I'm going to go through the main bullet points pretty carefully because Lambdas are a bit tricky when it comes to Java. In other words, Java has never had anything quite like these before, and so they deserve close attention. We're looking in my Emacs editor at the working file lambda basics wrapup.txt. So let's start with the definition. We've gone through it a couple of times, but lambdas are always unnamed, or so-called anonymous functions. They can be referred to, but they're still unnamed. But lambdas share something with the other function types in Java, namely methods and constructors. They can have an argument list that can be empty, and you can pass data and even references to other functions, including lambdas, to a lambda. So the data types of the arguments in the argument list is open. A lambda has a body. Technically, it could be empty, but that would be pointless, of course, because you want the lambda to do some work, and that work is done in the body. Very often, of course, we've seen the body is a very simple expression, and that's good design. The simpler, the better. A lambda has a return type, like any function, or void in case there is none. You can give that return type implicitly. That is, we've seen examples where you have something like n1 times n2, or n1 and n2 are both ints, and so the compiler can infer the return type. But there always is a return type or void in case of none. So again, a lambda in that respect is just like a method. So this next point just illustrates. In this case, we've seen this lambda before. The return type is an int. Its value is n1 times n2, whatever those arguments happen to be. And here there's an explicit return statement. Once again, the compiler is going to infer that return type. Now, just to review, you can have lambdas that are explicitly referenced. That is, you have a variable that refers to them, or they can just be used as is. So the example we've been using is this sort of thing, binary int op, where that's a programmer-defined interface type. The reference is mul, and then on the next line, of course, is the lambda itself. So the lambda remains unnamed even though it's referred to. Even explicitly referenced lambdas still count as unnamed function. So you can take a lambda, it can take basically anything as an argument. A lambda itself can be an argument to other functions. And of course, functions that take other functions as arguments are so-called higher order functions, and we've seen examples of that already. Lambdas themselves do have a data type. They're basically instances of various functional interface types. And as we go along in this screencast, we'll have occasion to see some of those built-in functional interface types. For example, there's one called java.util.function.binary-operator. We'll be taking a look at that one later on. You can also have, as we've seen, programmer-defined interface types. So for example, binary int op. My 2 cents, my preference, and my recommendation actually is that whenever you have a programmer-defined functional interface, that you use the annotation at functional interface. You write some code today, it works perfectly fine. You don't look at it for 6 months, you come back, you see that functional interface annotation, you remember exactly what that thing was for. So I find it very convenient and basically just an easy way to document. The big requirement, of course, for these functional interface types is that they must declare exactly one abstract method. Now what that means, and we've seen this as an example, there are various standard library interfaces. We saw the example of Runnable that already count as functional interfaces. The Runnable interface declares one abstract method, run, returns void, takes no arguments, and so that is thereby a functional interface. And there are many others in the standard Java libraries. That's the wrap-up. Lots of details. As we use lambdas in more and more examples, of course, the syntax will become secondhand. It will become natural. But for review, this document, I hope, proves useful. In this lesson, we're going to look at two other parts of functional programming in Java. Our focus so far, of course, has been on the Lambda, but we're now going to take a broader look that includes constructor references, more on that in just a moment, and method references. So constructor references, method references, and lambdas are the three big new additions to Java 8 with respect to functional programming. We're also going to get our first quick look at streams, another important innovation in Java 8. So we're looking in my Emacs editor at the source file refsexample.java. This will be included in the working files. So let me do an overview first, and then we'll dig into the program details, and then we'll actually run the program. So here's an example of a method reference. Num is a class. In fact, it's right down here. And dump is an instance method inside that class. You can see it here. So the reference to that is just num, name of class, colon, name of method. And we'll see how it's used momentarily. Here's a rather weird looking constructor reference. I say weird because it looks as if there is no constructor. Here is perhaps a more familiar looking constructor reference. So employee is a class, and we would use new with the employee constructor to create an instance of that class. But recall in Java, you would also use new to create an instance of an int array. And that's basically what you have here. For all constructor references, whether they're used for arrays or just regular classes, they're really factories. So what they're used for is to generate instances of arrays, instances of employees, and so forth. Let me jump now down to the example. I've got a very simple Pojo class, num. It's got a value, and there's a couple of other methods. Dump is the method that we're going to be using in the method reference example. I've also got some, by now familiar, functional interface. The first one I call a nums maker, and notice it has again a single abstract method declared. It's called make nums. It takes a number and it returns an array. So as you'd expect, this is used to create a new array of these instances. I've also got another functional interface called nums filler, and it's used to populate an array. So you would use a nums maker to make an array, and then a nums filler to populate it with values. So we just don't want the default value of 0 in that array. I've got a constant up here, how many, that's how big my array is going to be. And so let's jump now down to the actual demo code, and let me get it centered in the editor. I have the nums maker functional interface. I now have a reference named nums factory, and I use the constructor reference num array colon new in order to get an instance of the factory. The factory then is going to be used to create the actual array of nums, and that's done in the next line. So it's a little bit new in terms of style. What we've done basically is really separated the labor. So this represents separation of concerns. We have a maker, which creates instances of num arrays, and we have a filler that we'll see momentarily to fill those up. We create a maker here, that's a factory conceptually, and then we call make nums in order to create the actual array. So we now have an array, and it's of size 24 because that's the argument passed to make nums. Let's come down here to the filler. For the filler, I'm using a lambda, and the reason for that, the motivation now has more to do with design. This basically is a one-time function. I'm never going to use it again. I don't intend to use it for any other purpose. So once I have a reference to it in filler, I don't actually need it hanging around. So a lambda is perfect. So a filler takes two arguments, an array, and then how many elements to fill it with. So this is a slightly richer example than we've seen before in the bodies. So I create an instance of a random, then I go through a loop and basically populate the array with instances of num, and for each one of these, I set its value to a randomly generated integer, basically between 0 and 99. I'm just trying to make the integers more readable. Once I have the filler in place, so it's now defined, I can use the filler to populate the sum nums array with how many. Now we're going to get our very first look at streams. So for right now, a stream is simply a very lightweight iteration mechanism. So any Java collection can be streamified, and the way we do that is as follows. So here you can see I'm using the utility function, arrays as list. I pass it an array, and that's because I can streamify a collection, but technically not an array. So I first have to turn some nums, which is an array, into a list. I can then streamify it. You can see the pipeline coming here. Then I'm going to take this stream. The stream, by the way, is sometimes described very nicely as a conveyor belt of items. So basically, it's going to give me each one of those nums in that list. It's going to deliver it out, and we're going to send it to filter. Filter is a higher order function. It takes a function as an argument, in this case, a lambda. So what I want to do for each of those streamified nums is check whether its value is odd. So I've got isOdd defined up in num, but any function would do, and anything that passes the filter is then piped into for each, and for each, as you can see, is also a higher order function. It takes a function as an argument, in this case, num dump, and this basically prints out the number with some information about it. So that's really our first look at how lambdas and method references can be used within a data pipeline, if you like. Now let me jump out to the command line prompt, and I've already compiled the example. Let me now run it for you. So as you can see, I get a bunch of randomly generated values, and we can eyeball it to see all of the ones that are printed are indeed odd. They better be, otherwise there's something badly wrong with my code. I do it a second time. I don't get quite the same number. You'd expect that. Let me clear the screen, and we'll do it once more for good measure. And once again, we get slightly different values than before. So the filtering is working. Everything seems to be working very nicely. Let me jump now back into my Emacs and just make a final pitch for this last line. Now, the first time you see something like this, it looks, of course, complicated. It's relatively new syntax, although the cascading of methods is familiar in Java. We do this sort of thing a lot, but we're going to be doing a lot more starting with Java 8. So again, here's the short version. We basically take an array, some nums, and we turn it into a list because we want to streamify the list. That is, iterate over it in a very efficient way. More about that later. Each item, and each item is a num, an instance of the num class, is passed into a filter. The filter checks whether the value of that num is odd. If not, it discards it. If so, it passes that number on. It passes it on to for each. For each is another higher order function. It takes dump as its argument, and dump basically generates the output that we saw on the screen. This is now a more realistic context for how the functional programming constructs in Java are used. This lesson is a very quick review of the three programming constructs that make up functional programming in Java. And all three were introduced, of course, in Java 8. So the three are the Lambda, method reference, constructor reference. So let's go through each very quickly, and we'll recall some earlier examples. So the lambdas are clearly the most radical departure from conventional Java, that is Java before Java 8, because they allow you to do things that were, well, to be frank, unthinkable in earlier versions of Java. So let's go back to our sort example. We have an array called nums. We'd like to sort it. And what we can do for the comparison routine is just drop a lambda right in there. We have two arguments. They're named, but they're not typed explicitly. We leave it to the compiler to figure that out. The return value is not expressed explicitly. It's by implication. It's n2 minus n1. This, of course, gives us a descending sort because what we're sorting are ints. If we want an ascending sort instead, it's trivial to change. We just put n1 first and subtract n2 from it. So the big advantage of lambdas is that they're short, they're clear. As you can see in this example, you can just drop them in wherever they're needed. And you do that presumably because it's not reusable code. It's just a little bit of functionality you need right here, right now. You don't intend to use it some later time. If you did need to reuse it, you could, of course, have a reference to it. And we could drop the reference in here instead of the lambda itself. Now, this style of programming is familiar to anyone who's worked in a dynamic language. JavaScript, for example, has lambdas. The name isn't lambda, it's function. Other dynamic languages, Perl, Python, Ruby, also have lambdas. Ruby, for example, uses the keyword lambda. Perl uses sub. So there are different ways of indicating at the syntax level what a lambda is. Java has a nice clean syntax. I'd argue if you look at this line right here that it's hard to imagine anything simpler than that lambda. It's really well done, and I'd like to applaud the designers for that. Nicely done. Now, there are also method references, and we all know from doing object-oriented programming in Java that you have a class, you encapsulate methods in order to operate on the fields typically in the class. So methods tend to be reusable. They have a permanence that you wouldn't expect to have from a lambda. But there's no hard and fast rules here. So for example, earlier we did this. We had arrays as list. Some nums is an array. We convert it to a list. We streamify it. We then filter it to pick out the odd nums in that list. And then for each of those, we dump it. So num : dump is a method reference, and it prints out the value of the number together with its parity, whether it's odd or even. This method might be used in other places and other contexts, but it fits in very nicely here as an argument to for each, and for each, of course, is a higher order function because it takes a function as an argument, in this case, a method. In the line underneath it, I've added this, and now instead of picking out the odd ones, I pick out the even ones. And now in the for each, instead of having a method reference, I have a very simple lambda. It takes each num and it prints out its value. So there are many occasions where you might use a lambda, you might use a method reference. It really depends on the context. There's no hard and fast rule here. Method references and lambdas in general are very closely related, and there are times when you might replace one with the other. It's really a matter of convenience, overall program design, and so forth. Constructor references are a bit different, and they're a bit trickier because basically what they do is work off of the so-called factory pattern. So let me review the example that we saw earlier. We've got a functional interface. It's called numsMaker. It's got a single abstract method called makeNums. makeNums takes an argument. It basically specifies the size of the array. Now, for an array, a constructor is relatively straightforward. All elements in the array, of course, are of the same data type. So really, the only thing you can parameterize in an array is how many things are in it. You could, of course, later on set what the default value is going to be, that sort of thing. But in general, what you do with an array is set the size and you're done with it. And that very simple pattern is reflected in this example. We have the interface. We're now following a pattern that we've seen before. There's the interface type. Here's the reference name, nums factory. And the constructor reference is num array and : followed by new. In general, constructor references are going to be data type : new. So once we have the factory, we can now use it. In this case, it's used only once. We create one instance, using the nums factory, but we could, of course, create many instances. Instead of this particular example, let me point way ahead to something we'll do later. Imagine you're in a situation where you want to generate multiple messages that are to be sent to some destination. It would be nice to have a message factory with very clean syntax that you could drop into a pipeline. That's a bit beyond what we're ready to look at right now, so I'm really looking ahead, and we'll come back to pick up this theme later. This lesson provides overview for some forthcoming examples. We're going to focus in this lesson on streams and functions, and the working file that we're looking at in my Emacs editor is called streamsandfunctions.txt. So here's the big picture. Java 8 adds two major features: functional programming, and that's where our focus has been so far, and streams. Streams represent, in effect, a lightweight approach to iteration. The two go very, very well together. They're extremely closely connected. The Stream API in particular has many higher order functions, and of course Lambdas and method references are perfect to plug into those higher order functions as arguments. So streams become an ideal context in which to discuss Lambdas, method references, and constructor references, and we'll see lots of examples that do exactly that. So let's take a look at stream basics. Streams are closely related to collections, and we're all familiar in Java, if we've worked in it for a while, that the approach to iterating over collections has changed. Right from the start, Java had an enumeration type. Later, starting with Java 1.2, you got the iterator. And now, in more recent versions of Java, starting in 5, you even get the implicit iterator. So here's a familiar example. You have a list, let's say, of integers, and what you can do in a so-called for each loop is you provide an iteration variable, so in this case n, and you provide to the right of the colon a collection, and you automatically iterate over the members of that collection. If the list is empty, nothing happens. If the list has 1,000 things, then 1,000 integers are printed out. Now, starting with Java 8, we get the Stream API. The Stream API does the same thing, or can be used to do the same thing that is done right here, but it's a cleaner, easier way to do it, at least in my view. So here's the same example done, in effect, using the Stream API. So we have the list. Next comes stream. That streamifies the list. In other words, what it's going to do is provide a conveyor belt of the integers in that list. They're going to be delivered to us one at a time as needed. This is sometimes called lazy evaluation. In other words, right in the middle of the iteration, we could stop. There's no harm done, because the items from the list are given to us only as we need them. And in this case, we need them for doing printing. So we have here, of course, a method reference, and the stream basically pipes the items into for each. For each is a higher order function, and this is where the intimate connection between streams and the new functional constructs in Java 8 becomes, I think, most obvious. In general, any of the Java collections can be streamified, so you can do this lightweight or implicit iteration using streams. It should also be noted that streams are very familiar in operating systems. For example, nowadays, when you read from a file, you're really reading from a stream whose source happens to be a local disk file. As mentioned a moment ago, streamification is lazy. That means it's efficient in Java. It's not like the whole stream is generated at once. Or to put it in different terms, don't think of a stream as another collection. It isn't. It's not a copy of a collection. It's an iteration over a collection. So here's a very simple depiction of a stream with some suggestion about what can plug in where. So we have a collection of anything, could be customer information, that sort of thing. We streamify that collection. The data then go into filters, processing elements, and then at the end into collectors or accumulators. This is sort of a standard model of doing things. And of course, We might have as many filters as we like, as much miscellaneous processing as we like. So the examples are unlimited, really. There's all sorts of things you can do. The Stream API, by the way, is extremely rich. Java has all sorts of different ways of filtering, collecting, and so on. It's really a very, very powerful library now. Let's look at a couple of examples just to get the idea. So I have a list, and we're going to see this in a forthcoming example. It's a list of integers, and for each item in the streamified list, I'm going to take that item, you can see I'm using here a lambda, and map it to another list, and that list is going to consist of the integer's predecessor, itself, and its successor. So this is just proof of concept. So for example, the integer 4 would now become the mini list 3, 4, 5. The integer 5 would become the mini list 4, 5, 6, and so on. So here's a depiction of what happens. We streamify the list of integers, we do a mapping operation, and as you can see, if you come back up here, the mapping operation in this case, very simple, takes a very simple lambda. It's perfect for this case. It's a use one time and then throw away function. What it does is generates this mini list, and this mini list is then passed on to for each, and for each is a higher order function. It takes a method reference print line in this case as its argument. So each of these mini lists is going to get printed as such. That's the overview then of how streams and functions work together. What we're now going to do is refine this. We're going to dig deeply into the details through a series of examples. This lesson uses some short examples to illustrate the Stream API. We're looking in my Emacs editor at the source file streamof.java. It compiles and runs in the usual way, and near the end, we'll run it. So let's go through the imports very quickly. This is the stream interface. As we're going to see, it's got a convenience default method called of, which I'm going to use in the first example. The int stream, as you might suspect, is going to generate a stream of integers, very convenient, and collectors are used to collect the endpoints of streams. In other words, the idea is that you can send data items flowing through a stream, and then at the end you may want to collect them. To take a very simple example, you could have a stream of integer values and you want to double each one of those and collect those in a resulting list or other structure. So collectors are used for that purpose, and in this particular case we're going to generate some lists. So let's jump down to the demo section, and you can see stream of, the convenience method just mentioned, and it takes any number of object references. In this case, I've got the names of the partners in comedy routines, all caps, so there's a little bit of shouting here. We're going to fix that, and we're going to create a stream of that, as you'd expect. And the data items, one by one, are going to be passed into the filter method. Filter is a higher order function, as you can see, because its single argument is a lambda. And what we're checking to see is whether the string ends with a y. So if it does end with a y, for no particular reason, just for illustration, what we're going to do is convert that string, transform it to a lowercase version. So for example, Ray and May are going to be lowercase. We're going to collect everything that makes it through the filter and through the mapping so that we can sort them all. So in this particular case, Ray precedes May in the original list, but May is going to precede Ray in the sorted list. And then for each of these, we're going to print out. So you can see you have a lambda, you've got a method reference, and then another method reference. So these new functional constructs just go hand in glove with the Stream API. Let's look at a second example, the int stream. This is very convenient. I'm going to create a range of integer values 1 through 64, so the first number is included, the last number is not. So it's 1 through 64. And what we're going to do is filter these one at a time to determine if they're odd. So I'm just doing a bitwise AND with 1. So if you wind up with 1, you're odd. If you wind up with 0, you're even. And once again, for each of these, do a printout. So the familiar pattern is starting to emerge in this Stream API, higher order functions. In this case, filter and for each. In the first, we plug in a lambda. It's a one-off sort of function. And in this case, we could use a lambda, but print line makes perfect sense, so we throw it in. Here's a slightly richer example because it uses collections. We're going to have stringified nums, starting once again with an int stream, same range as before, but this can be tweaked obviously. We're going to filter for the odd numbers, and then we're going to call yet another of these higher order functions in the Stream API, map to obj, so map to object. So we're going to take that number and basically concatenate it with odd, so we basically get a string out of an integer, just as proof of concept. And then at the end, we're going to do a collection, an accumulation, if you like, aggregation. Different terms are going to be used, and collectors to list is going to give us a collector that knows how to create a list and is going to build the list one at a time. So at the end, we're going to wind up with a list of strings. Now, I'm going to take those stringified nums, stream those, and do a very simple for each, and for each of those, do a printout. The next example does a sort of reduction operation. So once again, we start with the int stream for convenience, same range as before. This time we're going to pick out the even numbers just to do something a little bit different. And we're going to reduce them to an average, and then we're going to take that average and convert it into a double. The reductions are going to be common themes in the examples that we see from now on. And then at the end, a simple system out print line. By the way, this last line, of course, we could have done this in a functional programming style, but sometimes it's just more convenient to do it the straight old-fashioned way. So as you're learning this API, don't give in to the temptation to do everything in functional programming. Some things in Java still make sense the old way. The more examples that you see, the more examples that you do, the more you'll develop your own style. So at the beginning, I think it's really important just to take a very casual approach to this. Try to use the streams and functions where they make sense, but the old ways are sometimes better ways. So this last example does yet another reduction. So the int stream as before, once again, we're looking for odd numbers. In this case, this is really straightforward. We just reduce that collection of integer values to a single integer value, the sum. Now let's jump to the command line very quickly just to see the code in action. I've compiled, and now let me just run. So you see may-ray, we talked about that a little before. We're now getting various streams. This first stream you see is of the odd integers, and then near the bottom of the screen where you see, for example, 39:odd, that's the stringified version of those integers. And then down at the very bottom, you see the average and the sum as computed. So that's a first look at the Stream API. It's some convenience functions provided in that API. This lesson continues the short examples that involve streams and the functional programming constructs, both of which are new to Java 8. We're looking at the working file called group.ex.java, and this particular set of examples focuses on reducers, collectors, and groupers. And we'll see examples momentarily, but first we need some data to work with. So I've got a very simple Pojo class called num. There's an enum called parity with the obvious meaning, even and odd as the values. There's a very simple constructor. There's a set value and get value, so a value property. There is a getter for a parity, and then there's a dump, which basically prints out both the value and the parity of a particular number. So almost any sort of example could be used, but the simpler the better in this case. So this very simple Pojo class will put instances of this into a collection and then do some operations on them. So this is the public class grouped by EX. Let's move down to the demo section. So what I want to do is get a sequence of randomly generated values. I don't want to use the int stream that we've seen before to get a range. I want something a little bit richer. So I simply create an array. In this case, we've got 64 in there. I populate the array with randomly generated integers, 1 or 2 digits just for readability, and then listify that array. Streams work on collections, they don't work on arrays, so we need to turn this array into a collection, in this case, a list. By the way, these operations could have been done in functional style, but in this case, my 2 cents is that it's just as easy and clear to do them the old-fashioned way. Now let me jump down here to the first example. So this is called total for all easy. So what I'm going to do is a reduction operation in the straightforward, obvious way. So we've got our list of nums. We streamify it. So this is the iteration. For each of these, we're going to extract the value of the number. This is a primitive, of course, an int, and then we're going to sum all of these. So at the end, we get a single value. This is a typical reduction operation. We take one thing, a list of num instances, and we reduce it to another thing, in this case, a single value. Now I'm going to do it again in a harder way for this particular example, but also in a more flexible way, because I want to get out on the table the reduce method that's part of the Stream API. So once again, the list of numbers, we streamify it, we get the value, and now you see reduce a little bit trickier. Reduce takes 2 arguments. Reduce is a higher order function because the second argument is a function reference. In this case, it's a lambda because a lambda makes perfect sense here. So the first argument is called the identity. Basically, it's the initial value for the reduction, in this case 0, because we're going to generate the sum. And it's also the default value in case the stream should run dry, but needs another value to complete a computation under the hood. The second argument is referred to in the documentation as the accumulator, and it's basically a function, in this case a lambda of 2 arguments. This is what's been accumulated so far, hence the name, and this is the next value. The accumulated value is the first argument. The next value to be gathered is the second argument, and in this case, the computation is straightforward, so far plus next. What you're doing in effect is you're updating the accumulator. So the accumulator is the current value plus whatever needs to be added. Now again, this is harder than the first way of doing it, just using the very nice sum method. But it's also more flexible because that second argument allows you to do anything that you might want to do. So you might want to do something richer than just computing the sum. And that lambda, as that second argument, gives you that flexibility. So reduce is a really important part of the Stream API. Another one of these wonderful higher order functions. And if you do the printout, run the program, you can confirm that you get the same answer in both cases. This next example does something a little bit more sophisticated, but the code is still short and sweet. That's the wonderful thing about these new APIs. So we have our list of nums. We're going to streamify it once again, but this time we're going to do a collection. We're going to collect the items, but we're going to group them, as you can see here, by parity. So basically what we're going to get up here is a map. The key is going to be the parity, odd for one, even for the other, and the value of the map is going to be a list of the numbers that are either odd or even. In the first example here, I extract the evens, and in the second case, I extract the odds. And then I call dump list, which is my own little utility function. And dump list does the obvious thing. It takes the list, streamifies it, and then for each element in the list, prints it out. Now I'm using a lambda here. It's 6 of one, half a dozen of the other. As noted in the comment, we could just use num dump because it basically does the same thing. So it's a style issue, absolutely nothing more. So let's go to the command line. Just to confirm that this thing actually does run, I've compiled already, and then you can see at the top, those are the two sums that were generated, one the easy way, one the harder way, using the reduce method. Then we get the parity examples. So in one case, we get all evens, in the other case, all odds. It better turn out that way or there's a bug. We've seen now in this second set of examples something a little bit richer. In particular, I would say the reducing and the grouping are really powerful in the Stream API. And we'll see more examples of those as we move along. This lesson covers a programming exercise. We're looking in my Emacs editor at the source code treemap.exer.java. I've compiled the code already and I'll run it shortly. First though, before getting into the details of the exercise, let's look at the big picture. Let's do a little bit of background. So we've seen some data pipelines, and they begin something like this. You might have, for example, a list of numeric values. You streamify that to do the iteration. Then you might do some filtering, some mapping, and so forth. And at the end, you might wind up with a reduction operation. So in this case, you would take the filtered values and reduce them to a single number, the sum. Another very common pattern is this. You take a stream, you do various mappings, maybe mappings together with filterings, and at the end, you aggregate the results. You don't want a single value, you want to collect the transformed values, and so at the end, you have a collect operation. Now in the stream, of course, you're going to have higher order functions such as filter and map, and then wind up at the end at some sort of collection or reduction operation. This exercise is going to focus on a collection operation. So let me do a very quick survey of what Java has to offer. The built-in library, java.util.stream, includes a final class called collectors, and collectors consist of a very rich set of implementations for the java.util.stream collector interface. So you have the collector interface, and then you have various pre-built implementations of that. Because you do have the interface, it's possible, of course, that a programmer might want to roll their own collectors, but I think this is not needed so much because the built-in collection is so good. In any case, if you were going to do a collector of the sort included in java.util.stream.collectors, you would basically have to define 4 methods because the interface consists of these 4. So there's a supplier, and this supplies the values to be collected. By the way, in the documentation, you're going to read a lot about result containers. So the collection at the end is called the result container. You'd need to define accumulator, and this is what would actually collect the streamified values into a container. So the supplied values are accumulated. You need a combiner. Maybe it's easiest to explain this with an example. Suppose you have a tree set or a tree map. So Java uses so-called red-black trees for this purpose at the implementation. And in these trees, you can think of them as having a left side and a right side. So you might do processing on one side or the other, perhaps both sides. What the combiner might do is take everything in the right subtree, copy it over into the left subtree, and make the resulting left subtree the combined tree. And then finally, there's a finisher that does whatever you might say post-processing is required. It does what the documentation calls a final transformation of the result container. These are not all that difficult to implement. You could have empty implementations if you didn't need any processing done, but we're going to focus on the built-in collectors and see how they work. So we've seen one already. So you have a list, you streamify it, and then you have a collect that looks like this at the end. Collect, collections, to list. Collections to list results in a collector that knows how to build a list out of those streamified values. Now let's get to some details. So I've created a very simple class called item. And for this demo, I have a static counter set to 6. And as I create items, I'm going to give each one of them an ID. I'm going to create 6. So it's going to be 6, 5, 4, 3, 2, 1 in that order. That's deliberate. We'll see why in just a moment. For good measure, each item also has a name. So this is a very simple Pojo class, just so we have some data items to work with. Now let me get down to the actual demo. So first I create an array of items because this is easy to do, and you can see there are 6 of them. The first one will have the ID of 6, then 5, and so on. And then down here, I'm going to make that array into a list because Stream works on collections such as lists. I'm going to map each of those items to its ID. So I'm basically collecting numbers, and then I'm going to collect these. So you see collectors, and now this is a little different, to collection, tree set new. So we have here a constructor reference, and we're passing that as an argument to collectors to collection. So basically, the items are going to be reduced, if you like, to their IDs, and the IDs then are going to be put in a tree set. Now a tree set should sort them. So even though they come in the order 6, 5, and so forth, when we actually do a dump of this, so for each of these now I'm going to do a print, and of course I'm using here a method reference, they should come out 1, 2, 3, 4, 5, 6. So let's jump to the command line very quickly and just run this. And as you can see, that's the order, 1, 2, 3, 4, 5, 6. So the tree set has done its job. Now the exercise basically is to change the collecting data structure at the end. I'm using a tree set. The idea now is to switch that over to a tree map. A tree map, of course, is richer but also trickier because a map is a collection of key value pairs. So basically you need a key and you need a value. So let me suggest that the value should be the item itself. In other words, an instance of one of these item classes is one of these, and the key, for example, could be the ID. Now there are different ways to do this, but I think you're going to find that lambdas are going to come in very usefully here in order to get the key. So you need a key, you need a value. As noted, there's any number of ways to do this. What I'd suggest is begin with the documentation, take a look at that. You'll see some very nice examples of this sort of thing. And then what we'll do in the forthcoming lesson is an assessment, a review. We'll talk about one way in which this might be done. So I hope you get a chance to try this. Most collections end with either reduction or aggregation. Occasionally you have examples where we do nothing but print something at the end, but mostly you're going to reduce or aggregate. So I think you'll find this quite useful. This lesson is an assessment of the Treemap exercise. Once again, we're in my Emacs editor. We're looking at the source file treemap exer_assess.java, and I'll run this momentarily. So let's start with the imports to see what's changed. We still have javautil.stream.collectors, so that's the built-in collector package. And I've also added javautil.function, function with a capital F. We're going to put this data type to use in forthcoming examples, but right now you're going to see a utility function that's quite useful for this particular example, at least the way that I've done it, and the familiar java.util.map, the interface for various map types. I'm going to use a tree map in this example. The item is completely unchanged, so I've not done any tweaking there. So let's go down to the demo. The first part of it is the same as before. In other words, here's the generated array of items. And once again, the IDs are 6, 5, 4, 3, 2, 1. So they're in descending order. This is what we did originally. We collect the item IDs by streamifying the array, then mapping each item to its ID, and then collecting these into a tree set. And the tree set, of course, is going to do the sorting. By the way, that tree set might then be used to build the map, but I'm going to build the map independently in a separate data stream. So for clarity, these are printed out, and now we get to the change. As noted in the exercise itself, there are many different ways in which you might do this, and so I've picked one, and we're going to focus on that one. So I'm going to create a map. The keys are going to be strings, and then the values are going to be the items themselves. We could pick, for example, the item name or some other property, but I'm going to put the entire item in the map as the value. So once again, we begin by turning the array of items into a list. So we do the listify first, if you like, because you can streamify a list, but not an array directly. And then, without any further ado, we go directly to the collecting operation. And now I'm using collectors to map, another one of these very powerful and very useful utility methods. ToMap, as you can see, is higher order because the first argument in this case is a lambda, and the second is another function call down here. So let me start with the top one. So we're going to take each item and we're going to map it to its name. And just for clarity, we're going to lowercase the name. So the names are things like item capital I-1 and so forth, but we're going to lowercase each name. Function identity, as the name might suggest, just returns an item. So the items come through the stream, they're collected, and function identity just yields the entire item. It's a very convenient way of doing this, and we're going to run into other convenient utility functions like this. In order to confirm that this has actually worked, we then take the items map. I create a key set. Of course, that's a collection. You can streamify a key set, and for each of these, just a simple print operation. For the values, once again, we go to the items map that's been constructed. We get the values, we streamify the values, we want to iterate over them. For each of those, we're going to map the name. So we're going to basically grab the name, and for each of those names, we're going to print it out. So these names are going to be capitalized because this is not the key, this is not the name used as the key, but this is the original name, which is part of the item. So let me jump to the command line just to confirm that this actually works. So I've already compiled Treemap exer assess, and I'm now going to run it. The top output you can see are the keys from the original key set, that's unchanged. And then the keys are just the lowercase names, and you can see they're in the order you'd expect, 6, 5, 4, 3, 2, 1. That's actually the entry order. And then the values down below are the original names of each item, and each of those is capitalized just so we can easily distinguish between the two. So as noted, there are many different ways in which you might do this. All of the Java packages that involve data structures tend to be very rich and tend to give you many different options. What I've tried to pick here is just one relatively straightforward way of handling this exercise. This lesson is about parallel streams, a really powerful part of the Stream API in Java 8. We're looking in my Emacs editor at the source file parallelstreamof.java, and that will be included, of course, among the working files. And I have about a paragraph of documentation at the top in which I hit on various issues. Let me summarize those issues. In a parallel stream, you have under the hood multi-threading. And whenever you have multi-threading, of course, you have thread safety issues. What we're concerned about from the functional programming part of all of this is thread safety. How can we make sure that even when we go parallel, which means multi-threaded in this context, how can we be sure that we still have thread safety? So let's start with some basic points and then move on to those issues. The streams that we've seen so far have been the default sequential streams. In effect, they've all been single-threaded. So for example, if you take a list and streamify it, what we've done so far is move directly into maps and filters and other higher order functions. And at the end, we typically have a reducer or a collector. We don't have this parallel construct, so there's no multi-threading. There's no parallelization. To go parallel is straightforward at the API level. So you could do list stream and then parallel, or you can use the convenience method parallel stream. So list parallel stream is the easier way to go. What happens now is that the stream, for example, list might be a stream of integers. That stream is effectively partitioned into substreams, and each substring is handed off to a separate thread. The idea here, of course, is to take advantage of multi-core machines. So if you have multiprocessors on a machine, you can have literal parallel execution. In other words, you can have multiple threads executing at the same time on different processors, each thread processing one of these substreams. The API is very powerful in that the multi-threading is done automatically and under the hood. However, there are still two big issues for the programmer. The first issue, of course, is this: is the task at hand something that can be handled in parallel? So let me take a simple example. Suppose that this list of integers needs to be processed in order, 1 through some higher number. If you partition the stream into substreams, you are going to lose that ability unless you impose some synchronization or other mechanisms. In other words, the task might not be suited for parallel streams. And the other big issue, of course, the second one is, are we going to be thread safe? Are, for example, the Lambda functions or methods that are invoked from within the stream, are those accessing some shared storage so that we could have data races? So thread safety and appropriateness are two big questions that the programmer has to address. The Parallel Stream API doesn't do anything there. It does the multi-threading very nicely, but it of course assumes that the multi-threading is appropriate, that the parallel execution is called for. Now, let me make a point about how the multi-threading is done under the hood. When you use a parallel stream, basically what happens is the runtime takes a thread from something called the fork join thread pool. In fact, I can come down here to the import and show you that. So java.util.concurrent fork join pool. That's built when the Java virtual machine cranks up. So there's nothing that we have to do. And the number of threads in that thread pool is typically, but this is not a guarantee, it's typically one fewer than the number of processors on your machine. However, you can have some say about that. Suppose, for example, that I'm on a machine that happens to have 16 cores, so 16 general purpose processors. I might invoke my app this way, Java my app -d. So the -d flag can be used to set the number of threads in the fork join pool. So I might set this to 9. I might have reasons for doing that. I've done some profiling and so forth. In general, if you take the default, if you're on, for example, an 8-core machine, it's likely that the size of the fork join pool is going to be 7. There is an easy way to find that out, and I'll show you that in this demo. So let's get down now to the source code. The API, as noted, is very straightforward. I have reference to the fork join pool only because I want to show you how to find out that number. I'm using stream once again, in stream, collectors, list. We've seen all of this before, so none of that changes. The API is very, very clean. At this line, I basically use fork join pool, common pool, get parallelism. That's going to tell you the number of threads in the fork join pool. In this case, on my machine, it happens to be 7, and I'm on an 8-core machine. Now to the demo. I'm using an in-stream for convenience. The range is 1, 1024, so remember that means 1 through 1023 are the values to be generated, and they're going to be generated in that sequence. That's important. We're now going to go parallel, so we're going to get the multi-threading under the hood. The stream is going to be partitioned. The runtime will determine exactly how that is done, and everything that follows now is going to be done in a multi-threaded way. So in particular, here's the filter. It takes a lambda as an argument. We've seen this before. It just checks to see whether a value is odd. If so, it sends it downstream. If not, the value is discarded. And the endpoint in this case is a very simple print. So we've got system out println, one of these method references that we've seen any number of times before. So the important thing is that different threads are going to be executing filter and for each. That's the key point. Now, if you come down and look at the output, I'm just showing you a slice, you'll notice that the values are no longer in order. So here's a 289, then a 641, then another 600, then we jump to an 8, then we jump down to a 65, then a 929, and so forth. And the reason, of course, is that the processing is happening at different paces. The stream has been partitioned. I don't know how many partitions there are. I'm guessing that it was probably 7, maybe it was only 4. I don't really know for sure, but there was a partitioning of the stream. This is what parallel does. And then the different threads did their filtering and did their printing, but this processing was interleaved. So it is now unpredictable about what the output is going to be. In fact, if you run this program several times, what you can expect to see is different output every time. If we need to see the numbers 1 through 1023 done in order, then this line, the parallel line, is no longer appropriate and we should comment it out. Let me make a last point about the fork join pool, because there's been quite a bit of buzz about this among programmers. So there are some implementation issues with the fork join pool, but let me make a general point about Java. Java has a nice clean separation of concerns between API. So we have the stream API, including parallel and parallel stream, very nice. And then we have the underlying implementation. And that separation, of course, always allows implementations to be tweaked, refined, improved. The problem with the fork join pool seems to be that if you get down to a single thread left in the pool, and if the other threads are blocking, for example, on I/O operations, you might find that the parallel execution actually degenerates into old-fashioned sequential execution, but with more overhead because you've got more threads involved that are just sitting around doing nothing. In ordinary applications such as this one, I've done some profiling on this one, that doesn't happen, but that's not to say it can't happen. The general point that should be made, however, is this. Java has been very good over the years at tweaking and refining implementations to work out problems. So I think it's fair to say that the parallel stream API is powerful, it's high level, very nicely done, and I'm confident that any quirks in the implementation are going to be worked out. So looking at parallel streams is really important, and in some forthcoming examples, we'll use them again. In this lesson, we're going to take our first look at the MapReduce programming model. MapReduce has gotten a lot of attention recently, particularly because of Apache Hadoop and other software products that implement MapReduce. As we're going to see, MapReduce is perhaps not the best name for this programming model, but the authors of the model, Google employees, were inspired by MapReduce in Lisp. And so we're going to take a look at the original inspiration, and then we're going to talk a little bit about what MapReduce now means. As noted, it fits in well with what we've been doing, functional programming in the context of streams, and in particular, parallel streams. The reason for that is that MapReduce might better be called scatter-gather. That is, take data, scatter it to different workers, go parallel, and then gather together the results, aggregate the results from those different workers. That's really what MapReduce is about in the current commercial sense. But let's take a little look at the original. This will help to reinforce some ideas that we've seen in Java functional programming. We'll get a better idea of where things came from. What I'm doing here is using a product called CList. It's from GNU, it's free. I've got the URL there if you want to try it. And so I'm showing you a very short session. In this session, the greater than sign is the prompt. So I've cranked up CLisp and I'm now typing stuff in. And the line below then is what I get back. So let's start with reduce. So this is very similar, you're going to see, with what we've been doing in Java. So in Lisp, Lisp uses, of course, so-called prefix notation. The function name comes first, reduce. And then we're going to use the operator, the multiplication operator in this case. I'm glossing over the syntax. We don't care about the list syntax. We care about the underlying ideas. We're going to apply multiplication to this list of numbers. In other words, we're going to reduce a list to a single value, which is the product of the numbers in the list. And when you run this, you get back a reasonably high number, so 654 million and change, and I've added the commas for readability. Now let's take the map part. So in map, the first argument is what we want in return. So this is basically a collector. We want our list as the result. Next comes a lambda, and this is fairly familiar. We've got an argument, in this case n, and here we've got what we want to do to each of those n's. And each of those n's is, of course, an integer value. We basically want to multiply n by 3 and then add 1 to it. So for no particular reason, I just want to do some transforming of the data in the stream, and I'm using the same stream as before. And you can confirm simply by eyeballing that this has been done. So the resulting list is 4, 10, 16, and so forth. Same number of elements as the original list, but the values have been transformed. Now we put it together. We do a reduce of the mapping operation, and we wind up with this humongous number. So that's the original map reduce in Lisp, but map reduce now as currently understood is a little bit different. It's really the scatter gather idiom in programming. And so to illustrate that, I'd like to do an overview of an example, the code for which we'll see in the next lesson. Let's imagine that we have some editors editing a book, and what they're doing is they're working on keywords. A lot of this nowadays, of course, would be automated. There are very nice programs that do this. So if instead of human editors, you want to think about these as programs, that's perfectly fine as well. And the idea is we're going to partition the pages to be considered into 4 groups. So we're going to go into parallel streams, if you like. So the first editor is going to take pages 1 through 50, the second 51 through 100, and so forth. So we scatter the work to be done among the editors. They're all looking for the keyword concurrent, and they come up with some results, which I've depicted in this little drawing here. So we've got the editor and the results, and the final phase, we've seen this already in Java, is we're going to do our aggregation, our collecting phase. This might be done all at once or in steps. So for example, maybe we aggregate the results of editors 1 and 4. They happen to be done first, and then 2 comes along, and then finally 3, and so forth. We have the scattering, the going parallel. We have the gathering, which is taking the results from the parallel streams in effect and collecting them together in some appropriate way. So this is the overview of the example that we're going to do in Java. It will involve, of course, streams, in particular a parallel stream, and it will involve, as you'd expect, some lambdas. In this lesson, we're going to continue with the MapReduce programming model, but this time by looking at a code example in Java. Let me start with the imports. We're in, by the way, the working file index.java. We're looking at this in my Emacs editor. I'll go out to the command line later to run the program. It's already been compiled. So list, array, list, map, we've seen this before. I'm going to use a concurrent hash map to store the book's index. And the reason for this is that we're in a multi-threading environment because of parallel streams. And we have to make sure that the entries to the index, they're basically going to be held in this concurrent hash map. We have to make sure that the entries are put in a thread-safe manner. So that obligation falls to us, the programmers. There's nothing in the parallel stream to guarantee that this is going to work correctly. We've seen collectors, and the thing to note right now is that the collector we're going to use is itself thread-safe. I'll come back to that issue in a bit. Now in this particular simulation, I'm actually picking up the MapReduce halfway through. That is, I'm assuming that the scattering has been done. So the job of assessing the index for a word such as concurrent has been passed off to the editors. I'm using more than 4 in this simulation. So they've done their thing, and now what we need to do is gather the results, and we're going to gather the results in parallel as well, because different editors may finish at different times, and we gather together whichever editors happen to finish their work. In the end, a complete index for the word is going to be placed into the concurrent hash map. So let's start with the code. This is the index, the map. So the key is a string, and then the value is a list of page numbers. They're going to be sorted in ascending order. That's a tradition, of course, in indexes. And here in the constructor, the index is initialized to a concurrent hash map. By the way, this is a very nice data structure. It's thread safe. It's also efficient. It's basically partitioned. So it's nice to have it take over the thread safety rather than having us do it ourselves. Add entry is really the key method. There's also a get entry, but add entry is the key part, and it takes 2 arguments, as you can see, a word such as concurrent, and then a list of pages on which that word occurs. Now, the only tricky logic here is this. When we get an entry, it might be the first time we have an entry for that word, or it might be the 10th time. And if it's the 10th time, then we need to aggregate the previous entry with the new entry. And that's handled in a straightforward if-else. The else clause is the clause where this is the first time we've seen this word, and the if part basically appends the new list to the current list. So the underlying logic needn't concern us. It's very traditional. Here we get some functional programming. Once we get this new list, either this first time or this appended list result, we need to sort it to make sure the pages are in ascending order. And once again, a lambda is absolutely perfect for this task. So I'm using the straightforward lambda that we've seen before. It's a one-off, basically, in this code. Now let me move down to index main. It basically contains main, and I'm going to take it top to bottom. So init is the basic scatter work. So I'm doing this manually, and I'm going to create a list of lists, as you can see here. So it's a list of integer lists. Each editor does a sublist. All of those lists are put into one big list. So you might say that's the work involved. And I've got, as you can see here, 8 editors. I'm putting them in no particular order, and then I'm returning this list of lists. That's basically my initialization to get the program up and running. Now, flatten I'm going to leave for just a moment and move down here to demo so we get a better sense of the flow of control. So we build the list of lists, and over there in the comment you can see what it looks like. I've simplified it. You've got a list and then sublists such as 7, 8, 9. That would be the first one, 1, 2, 3, and so on. The flattened version of this is going to take the members of the sublist and put them directly into the list. So flatten is a good term to describe this. And the Stream API contains a built-in method perfect for this called flatMap. And we'll come back to that in just a moment. So basically, we get a flattened version. So we're gathering together now all of the work from the various editors. We're flattening out these results. We create an index. We add an entry. In this particular simulation, there's only one add, but of course, there could be several. There actually is a second one. We've delayed a little bit, and somebody has come in late as usual, and so we take that new entry and add it as well. So as we'll see when I run the program that this works correctly, the add entry. Now let's look at this flatten, because it uses a parallel stream. In other words, it uses multi-threading under the hood. I take the list of lists and I feed it into a parallel stream. So now we get the fork join workers coming into play. The stream is partitioned into various substreams. Each of those substreams does the flat map. And the argument to the flat map, so flat map is a higher order function, is another simple lambda. And this is straightforward. Each n is basically one of these sublists, and all we do is stream that sublist to iterate over the members, and those members then are going to be collected. By the way, the collector here, generated by collectors to list, that collector is thread safe. So it knows how to aggregate together all the incoming results from the parallel workers. So this API really is quite powerful. It's really nice. The only thing we have to worry about is if we touch a data structure basically outside of the stream. And in this particular case, we don't do that because the adding to the index, the concurrent hash map, is done outside the stream. Let me go to the command line and just run this for you. This, of course, will be among the working files. So there's index main. I've compiled already. And as you can see at the very end down here, after the new addition, we get these 401, 402, 17, and 35. Those were the new entries. Up above, the initial entries were what came in from the editors who finished their jobs on time. And then that last editor was a bit late, so we had to do some last-minute additions. So this is a relatively straightforward illustration of how MapReduce looks in a very simple Java program. It also illustrates how parallel streams can be put to good use, and this flat map is just a wonderful addition to the Stream API. I find myself using it all the time, and collecting out of a flat map is absolutely straightforward. There's no threading issues here. Very nice, very clean. In this lesson, we're going to focus on the very important role that predicates play in stream processing. A predicate is simply a function that maps to a Boolean value, true or false. We've seen predicates already, but we've not really focused on the fancy name predicate. To gain some perspective, let's look at the big picture. So Java's Stream API centers really on two functions, or really families of functions because there are varieties of each. And these are higher order functions, filter and map. So they're parameterized, and of course the arguments they take are typically lambdas or method references. So the data pipeline gains its power from the fact that you can parameterize predicates, those are filters, and transformations, those are maps. So let's go back and look at a couple of simple examples. Some we've seen, some we'll see later. So here's an example of a typical filter. We've got an int stream generating numbers 1 through 64, and here we have a predicate. The predicate is basically an argument to filter. So filter takes this lambda expression, which lets the even numbers pass through and basically throws out the odd numbers. So this is a predicate in action, very informally defined. We're using a lambda. It's perfectly appropriate in this context. Down here is a familiar example of a map. It's a very simple one. We just take an integer value n and transform it to its successor. Nothing very fancy. Here's a slightly fancier example. We take an n, which is a list of numbers. In this context, it's a list in another list, so it's a sublist. But we take a list of numbers, and each of those lists is then streamified. So in effect, what we're doing is flattening out a list of sublists into a list of numbers. And we just saw that example. The power of the pipeline comes from the fact that we can interleave filters and maps in any way that we want, and we can pick any lambda or method reference that's appropriate as arguments to both filters and maps. So this is really high-powered stuff. Our focus now is going to be on filters, and as noted, these behave as predicates in the technical vocabulary. And Java happens to have a functional interface called java.util.function.predicate. It's a predicate, it's got a functional method. Functional method, by the way, is the fancy name for that single abstract method that you declare in a functional interface. In this case, the functional method is named test, but we can actually bypass it, and I'm going to show how in an example. So the Java predicate interface is a nice way, you might say, to formalize the use of predicates. And rather than try to explain this further in words, let's just jump to an example and focus on that. So I'm going to stay in the Emacs editor, but I'm now moving over to item.java. It's a very simple program that illustrates the power of predicates and the nice data processing patterns that you can develop using them. So once again, I need some data items, and I simply call this item. It's about as simple as it gets. An item has a name, and it's got an ID. I'm assuming that the ID puts an item in a category. So maybe everything with the ID from 1 through 9 is in one category, everything with 10 through 19 in another, and so forth. Here is what's really of interest to us. We have a couple of predicates. The first predicate is called isBeyondID, and notice that the way this is defined is a little bit peculiar. So we're returning a predicate for an item. So it's a predicate that is appropriate for an item, and the predicate itself is parameterized, takes an integer, and what it returns is whether an item's given ID is greater than the filter ID. So this basically is the filter ID. So for example, if the filter ID were 20, then items with an ID of 21 and greater would get through. Those with an ID less than 20 would not get through. I'm going to introduce a higher order function called filter items by predicate. It's going to take, as you can see, a list of items and a predicate and basically apply that predicate to the list, returning another list. So I'm going to filter by the predicate. This is very straightforward to do. We've seen this sort of thing before. So we streamify the items, we filter using whatever predicate we want to feed it, and then we collect the results together into a list of items and return that. So now let's put this to use. So I've got a very simple array of items, sort of silly, that's okay. We just need data, grist for the mill. We put those into a list, and now what I'm going to do is run some tests. So in the first test, we're going to filter with isBeyond for 20, and we should and do get all of the items because everything in that list has an ID greater than 20. And you can see the output there to the right. We're then going to do the same thing again. For 50, we should get only 2, and we do. Now, we have some powerful possibilities here. We're going to look at isBeyond 50 but negate it. So in effect, we're taking the complement. So what we get down here, as you can see, are all of the items whose ID is less than 50. So we get 4. 4 down here, 2 up here, exactly as it should be. We can also combine these predicates in Boolean ways. So here's an example. You see isBeyond 700. Well, that fails. There's nobody with an ID beyond 700 or beyond 30. And beyond 30, of course, picks up 34, 41, 52, 64, and 42. By the way, that OR is a so-called short-circuiting OR. So if we reverse the order, if you put 30 here, then you would have captured all of the 30 and above, and Java would not bother to execute the OR isBeyond 700. With an OR, this is a typical double vertical slash in Java. So that's a very first look at how predicates can be used to build, in effect, very high-level data processing pipelines. Of particular interest is this filter items by predicate pattern. So we provide a list or some other collection, could be a map, could be anything, and then we provide a predicate. And as you can imagine, we might provide more than one predicate. We might be able to compose a bigger predicate, a fancier one out of others. We'll see examples of all of that later on. For now, I just want to get out onto the table the basic idea that filtering by predicates and doing it in a formal way by using the predicate interface, the functional interface, has a lot of advantages. The resulting code is high level, easy to understand, but still quite concise. This lesson begins our review, a wrap-up, of how the functional programming constructs fit into the Stream API. Once again, the Stream API and the functional programming constructs tend to go hand in glove. The functional programming constructs work very nicely with the streams, and the Stream API is really designed with these new functional programming constructs in mind. So we want to take yet another big picture look at how these things fit together. There are many functions in the Stream API, but the major ones are really filter and map, and there are variations of these, of course. We've also seen collect, but the reason filter and map are so important from a functional programming construct is that we regularly drop functional constructs in as arguments. So in more technical terms, filter and map are higher order functions, so they take functions as arguments, and those functions as arguments can be, of course, defined as ad hoc lambdas or as something a bit more formal, and we've seen examples of both. So let's start with predicates. Predicates are so-called Boolean valued functions. They're basically tests, and they fit naturally as arguments into the filter function. So the filter method, part of the Stream API. Here's a very simple, I'm going to call this an ad hoc example from Stream of Java. So we just drop in a lambda that tests whether a given integer value is odd or even, and the ones that are odd we let pass through. We can also go a bit more formal. So we saw this in the item.java example. So here we can actually define a predicate as a method. So it's called isBeyondID. As you remember, this basically is used to filter items by their ID property. So isBeyondID takes an ID and then returns a predicate, and that predicate is defined, as you can see, as a lambda. Why not? This is the easiest way now in Java to define a function, so we might as well use this. So we have a function isBeyondID that returns a function as its value. Very powerful, very high order. We then applied that predicate in something called filter items by predicate. There could be other predicates as well. The first argument is a list of items, as you can see, and then the second argument is one of these predicates. We could have just dropped in a lambda here as an argument, but we've gone a bit more formal. Now, there are comparable data types for functions that are not predicates, and we'll have occasion to study those as well. So with respect to predicates, we can plug in lambdas, we can plug in method references to the stream function filter. Let's now look at mappers. So the job of mappers, of course, is to transform an incoming stream value and to push out some transformed value. We've seen various examples using both lambdas and method references. Both fit naturally in here. So here's an example from stringsreview.java. That's a forthcoming example. And this takes n, so an integer value such as 4, and it generates a list consisting of n's predecessor, in this case 3, n itself 4, and n's successor, in this case 5. It's also straightforward to drop in a method reference. So in this particular example, this is from the group by ex java.program that we've already considered. We map a incoming string to the lowercase version of that string. So to lowercase, of course, is one of the string methods. Constructor references are also quite powerful. They're not used quite as commonly as method references or lambdas, but an example we've seen from treesetxer.java was to construct a collector. So at the end of our data pipeline, we had collect, and then collectors to collection, what we want is a tree set. So this is a constructor reference. It's very convenient. In effect, it's a factory. What this does is create new instances of tree sets. Very straightforward, clean syntax in order to do this. So those are the big pieces. In terms of summarizing them, we have higher order functions in the pipeline. In particular, our focus has been on filter and map, and we can drop in lambdas or method references as arguments to those higher order functions. That gives us a lot of power because what we have now is a parameterized data pipeline. This lesson continues our wrap-up of how the functional constructs in Java 8, so lambdas, method references, constructor references, fit into the Stream API, also new to Java 8. In this case, however, we're going to look at Java code. So in my Emacs editor, we're viewing streamsreview.java, and I'll run this from the command line at the end of the review. So let's start with the various examples. I just want to highlight some features that we've seen, reinforce some key ideas, and also do a bit more in terms of tracing. So we start with a very simple example. We take a list of integer values, streamify them, the lightweight way to iterate in the new API, very clean, and then we simply map each value to its successor. So it's not a very exciting mapping or transform, but it is a transform. And then we use a method reference to print each out. So we've got the big pictures. We've got lambdas as arguments to higher order functions, in this example map. We've got a method reference as an argument to a higher order function. In this case, the higher order function is for each. In the second example, we start out pretty much the same way, but then do some filtering. So we plug in a predicate. The predicate is a lambda. It's an argument to filter. We then do a bit more in the transform. We've seen this a couple of times now. We just take an integer and map it to a list consisting of the predecessor, the integer itself, and the successor. And once again, we use the higher order function for each. In example 3, the only thing that changes really is the for each, and this shows again that in a lambda, the body can be any arbitrary collection of statements. In this case, it's still a single statement, system out format, but the idea now is we want to grab who the current thread is, what the thread is that is executing. The reason is this: the stream is sequential, and so we would expect that the thread that is doing this is going to be the main thread, and we're going to see that confirmed. In the next case, we go parallel. So this now brings the fork join thread pool into play. So the main thread is also in play. The main thread, for example, is executing this statement. It's the one that is causing the stream to go parallel. The mapping and the for each should now be done in parallel on a multiprocessor machine. This is a multiprocessor machine. So once again, I'm going to trace to get the name of the thread. We'll see the main thread in play, but we'll see other threads as well. This confirms that the parallel stream is doing what it's promising to do. The next example shows something that's a bit trickier, the reduce method. So once again, we do the parallel stream thing. We do the mapping, nothing new there. And now this is the 3-argument version of reduce. We've seen the 2-argument version. This is the slightly more complicated one. So the 3 arguments are these. 0 is the so-called identity. It's basically the initial value in this example. It also serves as a default value should the underlying runtime need a default value. The middle argument, a lambda, fits in perfectly here. So reduce is higher order. It's the so-called accumulator, and it's accumulating the items one by one. So as each integer comes in, there's an incrementing of the sum. And this is the combiners. So think of it this way. What we now have is things going on in parallel, doing accumulations. We need to combine the accumulated values, and this does it. We get 2 sums, and we combine them simply by doing sum1 plus sum2. Very high level, very intuitive, nothing complicated. It's an easy way to do multi-threading in the Stream API. And there are no thread safety issues here whatsoever. The next example does a bit more. It really does a trace. So what I'm trying to show here is where does the accumulator kick in? Where does the combiner kick in? And when we run this, we'll have occasion to see those details. The next example is a slightly richer example of mapping. So I've got various small lists. We've seen this sort of thing because what I'm going to do is create a list of lists. So a very rich data structure. It's going to be a list of integer lists. And of course, as you can expect, what we're going to do is to flatten that guy out. So the flat list is gotten by taking the list of lists, we go parallel, we do a flat map for each of those sublists. In other words, n is actually a sublist of integers. We stream that to get the individual members, and then we collect all of the members together into a single list. And that collectors to list call creates, of course, a collector. It's completely thread safe. So we don't have to worry about the underlying coordination. Let me now go to the command line to run this, and I'm going to pipe the output through more so that we can pause and look at some of the output. So the top examples are not too interesting. These are just the streaming and then the mappings. So you can see near the bottom of the page, those little sublists consists of even integers with their predecessors and successors. For example, you have -1, 0, and 1. That's the first example. Now we're getting into more interesting territory. At the top of the screen is the output from the sequential stream, and as you can see, it's the main thread that's doing all of the work. So I'm grabbing the thread and getting its name. Down near the bottom, it's now a bit more interesting. The main thread is doing some of the parallel work, but then there are various workers from the fork join pool kicking in. So worker 1, worker 6, worker 2, worker 5, and so forth. So again, my machine is an 8-core, so I've got 8 processors, and this means that the fork join pool almost for sure is set to 7. And in this case it is. We've confirmed that in an earlier example. Now we're looking at the breaking up of the accumulating and the combining activities in a parallel stream. So certain values are accumulated, added to a running sum in one thread, and then in the combines, you see that 2 threads are combining their results into one. And then at the end, we get the expected result. Finally, at the bottom of the page, we have the flattening. This is a very, very convenient sort of thing. It's common to be working with sublists. You want to take those members and basically generate one big list with everything, and FlatMap is wonderful. It's perfectly suited for that purpose. This lesson is an overview of a forthcoming code example that deals with customers from a fictitious company. Let me jump to the command line and give you an idea of what the data look like. So I've got part of the program here, and I'm going to run it. And you can see that starting from the top, there are various fictitious customers. So Fred Cruz 1 is the first, Fred Poe 2 is the second, Carol, Ted, Joyce, and so forth. And there's different pieces of information: credit line, total purchases, balance due, and the category of purchases that the customer favors. Now, all of the data are generated randomly from arrays. I don't want to rely on a database. I want this program to be able to run standalone. And there's sufficient data here to do things that are more realistic than what we've done so far. So the idea is to get something that looks like a real data-driven application. Altogether, I have 32 customers. It would be easy to increase that number arbitrarily, so we could raise it to 128 or whatever. But 32 will be enough, I think you'll see. Now let me jump back to my Emacs editor. We're looking at the working file customeroverview.txt, and once again, I'd like to start out with the big picture to provide some context. So we're in, of course, the big data world. The data sets that applications have to deal with tend to be huge. In the old days, databases might have dealt with huge data sets, but applications didn't so much. But now it's really the rule rather than the exception. And of course, it's easy to become overwhelmed in a big data world. So it's like, to cite the favorite metaphor, it's like trying to drink from a fire hose. So the standard pattern in dealing in a large data environment with large data sets is this: you filter the data, basically to focus on what you really care about. And of course, you may need many different filters because your application may have many different interests. You then transform the data. We've seen that a bunch of times. And then you do standard end of stream operations, reductions, collections. And collections often involve grouping. So we may want to take the data that we've already filtered, transform them in some way, and then group the results. And maps, of course, are ideal for that sort of grouping. We see this kind of filtering a lot in the database world. Virtually any real-world SQL statement, for example, is going to have a where clause. And the where clause, of course, is basically a filter. The idea here is to use this customer example to capture the pattern of filter then process as it occurs in the real world. We've already set this up a bit. We've talked about predicates. We've talked about the use of Lambda, method references, constructor references. So what we're going to do here is put everything together. Let me go down and finish with a brief overview of what a customer looks like. So a customer has a unique identifier, first name, last name, email address. There's randomness in the email addresses among email providers because we might want to filter by email provider. We're having trouble, for example, sending emails out to certain customers. We suspect that a certain email server may have been blacklisted. We need to find out. There's a favorite category. This is pretty silly. I've just got some random categories, so don't look for any deep meaning here at all. There's the customer's total purchases. So for example, we may want to have a rewards program for certain customers who've spent a lot. There's balance due, always an uncomfortable situation. And then there's the credit line, and the credit line is basically the max for the balance due. After you cross that line, of course, there is no more credit. That's an overview. We've had a quick look at the sort of data that we'll be dealing with. What we'll do in a forthcoming lesson is we'll look at the code, we'll look at filters, predicates, we'll look at transforms in detail. This lesson focuses on the source code for the customer app. The source code consists of 3 files. Customer.java is a POJO class, and customers have various properties, a credit line, first name, last name, that sort of thing. This is easily changed, of course, to add more properties or to tweak the existing properties. There's also an override of toString for convenience. CustomerLive.java is what we're looking at right now in my Emacs editor. This is going to be our focus because this is a library of sample predicates and collectors, and that's our interest right now. In this particular lesson, we'll be focusing on the predicates. Customer main generates customer instances and runs various tests. So we'll be looking at the output of those tests when we jump to the command line a bit later. But let's begin with the code analysis. For convenience, by the way, all 3 source files are in customers.zip, and that will be among the working files. So let me come down and start with what I'm going to describe as my driver. So I have a higher order function called filter by predicate. It takes 2 arguments. The first is a list of customers. That's again generated automatically in customer main. And the second argument is what makes filter by predicate higher order. It's a reference to a predicate that's applicable to a customer. That's quite a mouthful, but notice that predicate customer is just a data type for, in this case, as we're going to see, a lambda. What filter by predicate returns is a collection, so any sort of collection would work. In these examples, I'm going to use a list because that suits our purposes. So here's the body. We've seen this pattern before. We take the list and stream it, send it through the filter. The filter applies the predicate, which again is the second argument up here. And then any customers that make it through that filter are collected into a list, which is returned. So let's come down and now look at the predicates. And let me focus on the first one, but you'll see the pattern is the same throughout. We have a static method that returns a predicate suitable for a customer. Most are parameterized, but not all. So that's not of particular interest to us. Of interest is that each of these returns a lambda. So the first one just checks to see if the customer ID is greater than or equal to a given ID, that is an ID given as an argument. The next one basically checks to see whether the customer's email server matches a given email server. The next one takes no arguments. It basically checks whether a customer is in good standing, whether the balance due is less than the credit line. To begin, all of the customers fit that bill. This one checks whether a customer has a high credit rating and so forth. And then there's a fifth one. We'll get to that in just a bit. So each of these functions returns a predicate, and each of those predicates is suitable as the second argument for filter by predicate. So we're doing some higher order programming here. We've got a function that takes a function as a second argument, happens to be a predicate, and we've got a bunch of functions that return functions, in this case, lambdas that are suitable as arguments. Now let me do the last example. There are various approaches to writing these predicates. We've seen 4 instances where the predicates are returned basically from predicate producing methods, such as high credit rating. I'm now going to take a slightly different approach. I'm simply going to have an object reference, in this case a reference to a predicate for a customer. So I've got a couple examples. HCR is for high credit rating. We've actually done that already. I'm now doing it slightly differently. Here's the lambda. And then I have another called in good standing. Once again, that's been done already. It's now done slightly differently. And the reason for all of this is the payoff down at this line. So we have high credit rating in good standing, and that basically combines the other two. So you can see HCR and IGS. By the way, this chaining together of predicates could go on indefinitely. There could be another and another and another and. We've seen negate in an earlier example for the functional interface that applies to predicates, and this one now illustrates the and. We have a higher order function, filter by predicate, that we can use to test the predicates. We've got an object reference down here to a what might be called a composed predicate. And then we've got some samples up here of methods that return predicates. So let's go to the command line and let me do a quick demo of this. I've compiled the code. I'm going to run it and I'm going to pipe that through more so that we can look on the screen at the output. So in the first case, we're looking for IDs greater than or equal to 30. We can eyeball and see that that holds for the output. We're now checking the email server to make sure that everybody is under meta email. That also turns out to be the case. In good standing doesn't do much filtering here. I've not checked it carefully, but I believe from the randomly generated data that everybody is in good standing to begin. So we'll jump by that to get to something a little more interesting. Credit line greater than 30K. Again, we can eyeball and see that these predicates are working. And this is now the combo. So we're applying the reference together. We're checking both for high credit rating and in good standing. And this does do a little bit of filtering out. So that's a very quick demo. Let's return then to the source file. So we've looked at roughly half of what's in this customer library. We've looked at the predicates. What we're going to look at next are the collectors. This lesson continues the code analysis of the customer app. In particular, we're looking at the library functions. They're in the file customerlib.java, and this file is included in customers.zip, which is in the working files. Last time, our focus was on the predicates. Now we're going to look at some collectors, and then in an exercise, we're going to put these together. So I have some sample collectors, 4 of them in particular. Others, of course, are possible. And the first one does something that's very common in collecting. We're doing some grouping. So we're basically partitioning all of the customers that make it down to the collection phase. And the collection phase, of course, is typically the last phase in the pipe. So you're doing either collecting or reducing typically. And our focus now is on the collecting part. So in the first example, we're going to group the customers by email provider. So again, we take a list of customers and then generate a map, since a map is a natural way to partition. In the map, we're going to have the email provider as the key. That's going to be given as a string, and then the list of customers that have that email provider. So this is very straightforward. The grouping API, you might say, among the collectors is very rich. we're really just scratching the surface here. So the idea is not to hit each and every function that's available, but rather to get the feel for how these might be used. There's simply too much detail. It can become overwhelming, so we want to get a sense of what the pattern is. So in this first collector then, once again, as you'd expect, we stream the list. I'm leaving out the filtering for emphasis. We want to focus on the collecting part. So collect, again, takes a collector, and this is basically an instance of an object that knows how to collect things. And we're going to be grouping by knows how to build maps, and we're going to be grouping by the customer's email server. And this, of course, is a familiar method reference. By the way, this is an instance method, so the syntax is class name : get email server. Were this a static method, it would be class name period get email server. But this is an instance method in the customer class. The second example has some lambdas now in the collecting part because this is a little bit richer. So we're going to group by email provider again, but do it a slightly different way. So as you can see, for the collectors, we're calling Treemap and the 3-argument version. So the first argument returns the key. So a lambda does this. For each customer, we get the email server. That's a string. And then in this case, to change it up slightly, the value is now going to be get the full name, and I have a little convenience function in customer lib called get full name. It just does the obvious thing. It invokes the get first name, get last name, puts them together in a readable way to produce the full name. And then the third argument, we've not seen this sort of thing before in Treemap, takes 2 arguments, name1 and name2, and basically combines the 2 names. These would be the full names separated by a colon. So the third argument here, in effect, is an aggregator. So once we've gotten a couple of names together, how do we combine those? Well, we combine those by putting name1 together with name2. Remember, what we're trying to do is combine all of the names that happen to share an email server. So the lambdas are a nice, clean way to implement Treemap in this example. This next example I find to be very, very useful in practice. It's a group by favorites, and what we're going to get as the value of the map is a count. So once again, the customers are streamed into the collector. The collector once again does a grouping, and in this grouping, the favorite category, wines, skis, whatever, is going to serve as the key, and then a count of all of the customers who share that favorite is going to be the value. So basically, we're going to find how many people favor each category. This last one I've thrown in more as proof of concept just to get it out on the table because it can prove to be very useful, and maybe it's best explained simply by going through the details. So once again, the customer list is streamed into the collector. So we do the collecting and then. So we're doing a sort of composition. So we put all of the customers into a list. We've done that before, straightforward. The and then part, this might be called the finalizer. You'll hear that a lot in the documentation, is that we're going to render this collection unmodifiable. So in effect, we get an immutable list. So if we were to send this list further downstream in a pipe, whatever code happens to be further downstream would not be able to change this. Let me now jump to the command line. Let's do a very quick demo. So I've actually gone through the predicate section. I'm now about to begin the collecting section. So let's do that. So here we're getting the email providers, so you can see the various keys. And then the values, it's going to be a big array. In effect, it's a list, a big array of all of the customers who happen to have that email provider. By the way, the toString for the customers is kicking in here, so we get all of the information. Let me jump down a bit. This is the second version of email providers. So what's happening is first and last name are separated by colons, and then the different customers are separated by colons. I could have made this more readable by putting in double colons to separate the individual customers. And the last one, the favorites, is the one that I find very, very useful. The keys here again are the categories, movies, toys, wines, and so forth. And then down below you'll see the values. By the way, there is a bit of randomization in the application, so if you run this repeatedly, you're going to get different numbers for all of these. So we've now gone through the customer lib. We've seen both the predicates and the collectors, and what we're going to do next is combine them in a sense. This lesson presents an exercise that deals with the customer app that we've been looking at. In the customer lib file, and we'll jump to that momentarily, we've seen various predicates and basically two different styles for building those predicates. In one case, we had functions. They happen to be static methods that returned a predicate applicable to customers. So high credit rating was an example of that, and we'll go and look at it again momentarily. And the second approach was to take a reference and just set it to a lambda, but not within the body of a method. And the HCR-IGS high credit rating in good standing is an example of that. So let's jump back to the code just for a refresher. So you can see high credit rating up here. It's a method. It returns a lambda. So in effect, a predicate customer in this case. And down here you see HCR-IGS, which combines two other object references into a single predicate. So basically we have a composed predicate or combined predicate down here. Now, either approach is perfectly fine. My sense is that if you have an argument being passed into the predicate, as you do in this case, I find this approach to be somewhat easier and more flexible. Well, we'll see further examples downstream where you could gain the same flexibility in effect by using this approach. So it's not a hard and fast rule. There are two approaches. You pick the approach that turns out to be most comfortable for you. Now let me come back to the working file, which is filters collectors exercise.txt. We also used in that first example a so-called predicate driver or predicate invoker. It happened to be called filter by predicate. The second argument was one of these predicates generated in either fashion. In all cases, however, those predicates were placed as arguments to the filter method. Now, the point of the exercise is this. What you have in the collecting API for Java 8 are some collectors that actually take predicates as arguments. So in particular, what I want to look at is java.util.stream.collectors. So that's the class, again, that encapsulates all of these very convenient collectors. That class happens to have a partitioning by method, and that method accepts a predicate. It's very useful to take partitioning by. It's going to generate a map. And the key for that map, of course, is going to be a Boolean. It's going to be true for those customers in this case that happen to satisfy the predicate, and it's going to be false for those customers that do not. So it's a very, very convenient way to plug a predicate into a collector. It leads to, as you would expect, more concise code. So if you have time for the exercise, my recommendation is this. What you want to do is start by consulting the Java doc, the documentation for java.util.stream.collectors. In particular, you want to look at partitioning by. You'll find they have a nice example in there. And then you want to take that and apply it to our example, that is the customer app, and do a partitioning by where you feed it a predicate for a customer. In different terms then, partitioning by is a higher order function, as so many are in this environment. I hope you have a chance to take a crack at this exercise. I think you'll learn a lot by going through it. This lesson assesses the customer app exercise. We're going to get into the technical details of the exercise momentarily, but I'd like to start by taking a look at the motivation. What's the purpose? What's the point of this exercise? So the exercise to review is to use the partitioning by method, which is part of java.util.stream.collectors, in order to do two things. The first is to filter the customer stream, and the second is to collect the filtered customers into a map. And the idea here is to do it in one step, basically by using partitioning by instead of using a separate filter. Let's look first now at the payoff. So why do this? In other words, what's the motivation? And to do that, I'd like to jump down here to a general example. So we've seen this pattern now quite a bit. We have a collection, we streamify it. That's a very clear and easy way to iterate. I'd argue that there is no easier way to iterate. We then filter the streamed items, picking out the ones that we want. We may transform them in some way, and we could repeat this as needed. Now, one thing I think we'd like to do is this: get rid of the ellipses. Instead of having multiple calls to filter or map, the idea would be to take this filter and build it up to do whatever application logic is required. We've seen already how you can AND two filters together, in particular two predicate customers that we've been playing with. So you can build up filters as needed, you can build up maps as needed. The advantage is that the pipeline stays pretty short. The number of stages doesn't become overwhelming. Finally, at the end, of course, we do a collection. Sometimes we might do a reduction instead, but we're focusing on collecting. And the idea in this exercise is to eliminate the filter phase and basically to do the filtering and the collecting in the collecting phase. The idea here is that the pipeline becomes shorter, the code becomes more concise, it becomes easier, I think, to understand, particularly if you return to this code, let's say 6 months from now, and you're not quite sure what was going on. Looked at a different way, where we put our effort is into building the filters and the mappers that we need, and then we plug them into a stable pipeline as needed. There's no magic here, of course. Everybody who programs knows that. It's not as though the problem has become simpler. It's that we've distributed the complexity of the problem in a better way. So these higher order functions, filter and map, are really, really convenient because they allow us to parameterize and to keep the general structure of the solution constant, permanent, short and sweet, we hope. Now let's look at the details. So what I have is a file called customerlib.exer.java. It's the same as customerlib.java from before, except it includes a solution, one solution to this exercise. I've put this in a zip file along with the text file we just looked at, and that zip file is called filters collectors exer assess.zip. Quite a mouthful, but you'll find it there in the working files. So let me give you the overview. What I'm going to use is this predicate right here, high credit rating, or I should say this method that returns a predicate. So it returns a predicate down here, a lambda, that basically tests whether your credit line is above a specified value. And that value is up here, min for high. So the solution I have is down here. I have something called partition by credit rating. As you can see, it returns a map. The keys are booleans, false, true, and for each there's a list of customers. So conceptually, false would be the list of customers who don't have a high credit rating. True would be the list of customers that do have a high credit rating. And partitioning by is illustrated here. So we take our usual customer list, stream it. The filter phase is now gone. There's only collect, but we're using partitioning by. Partitioning by expects a predicate, and here we make a call to customerlib high credit rating threshold, which of course returns the appropriate lambda, and that lambda serves as our predicate. So let me jump to the command line. I've already compiled this and run it down to where you can see it near the bottom of the screen, partitioning by credit rating. You can see the two keys, false and true. So basically, the values list is going to be two sublists. The first sublist will be those who fail to have a high credit rating. So you can see, for example, for the first one, the credit line is 18,000 and change, 26,000 and change. I set the cutoff, by the way, at 40 for this particular experiment. And if we come all the way to the bottom, what you're seeing is the second sublist. So you can see 43 and change, 44 and change, 40, 40, 43. So basically, we get a nice convenient map, and this of course could be further partitioned. We might want to have further categories, and that would be yet another exercise. So let me jump back to the Emacs editor. What's very nice about the Stream API, just like the new functional programming API, is that it has lots of built-in things to help us do what we need to do. And I think you'll find that partitioning by is particularly useful. It's a useful way to combine filtering with collecting. This lesson returns to a topic that we've considered before, the functional interface. The difference this time is that the emphasis is on built-in functional interfaces. In other words, types that ship with the standard Java libraries. We're in my Emacs editor. We're looking at the working file moreunfunctionalifaces.txt. Let's start with a review of what we've seen before. In the very first code example, we've seen this annotation, java.lang.functionalInterface. This is a so-called marker interface. It's used to indicate that some other interface counts as a functional interface. So we could remove this line and everything would work out just fine. The interface itself that's being marked is called binary int op in this first example. Any name would do, of course. And the critical requirement is that a functional interface declare, not define, declare a single abstract method. So abstract can be put in there optionally for emphasis, as is done here. But the important part is that a declaration ends with a semicolon, not with the braces. So if you have braces, you're defining the function. If you don't, you're declaring it. So the declaration is right here. The next line for proof of concept defines a static method in the interface, but this has no impact on the status of binary int op as a functional interface. So we could remove this line, the static line. We could remove this line, the annotation, and we could also remove the keyword abstract, and everything would still be just fine. There are various interfaces in Java. We looked at this one, java.lang.runnable, that count as functional interfaces, even though they predate this annotation. So java.lang.runnable counts as a functional interface. There's one little cute feature here. Functional interface itself is not a functional interface. Let me explain what I mean. If you take this line of code and try to compile it, the compiler comes back with the cute error message saying that functional interface, capital F, capital I, is not a functional interface, 2 words, because this particular interface does not declare an abstract method. In fact, functional interface is empty. It doesn't declare any methods. Its job is just to mark other interfaces as functional. Let's now turn to what's really of interest to us in this context after that very quick review. So there are about 40 built-in functional interfaces. They're in java.lang.function. If memory serves, the current number is 43. We've seen one of these in an example, predicate, which is generic. You can set the type, and we use predicate customer, of course. It has subtypes, specializations such as double predicate and int predicate. So we're going to see a lot of generic functional interfaces such as predicate, and then specializations of these such as double predicate and int predicate. Also, you're going to notice that some of the interfaces end with function and some end with operator in their names. So let me use an example to clarify what this is all about. There's something called the Bifunction. We're actually going to see a code example of that. It takes 2 arguments of any data type at all. They don't have to be the same, and returns a result of any type. So you could have 3 different data types involved in a bifunction. And as such, a function, of course, could be defined as a lambda. That's the easy way to do it. A binary operator, by contrast, also takes two arguments and returns a value, but all three are of the same type. So a binary operator is, in effect, a restriction on a bifunction. And we'll see other examples of this naming convention. This lesson is a code example of two built-in functional interfaces. The name of the file is intro.bifunc.java, so that's the source file. We're looking at it in my Emacs editor. And the two imports of interest are these. You see bifunction, that's the more general type, as we'll see, and binary operator, that's a constrained specialized type, and we'll see examples of both. For good measure, I've included the original code example with a functional interface called binary int op. I've simplified it back to its original form, so we have only the so-called functional method called compute, the abstract method. And now let's get to the main class and take a look at it. I have two arrays. These are going to figure in a later example, so I'm going to pass over these very quickly. And then in the middle, I have two higher order functions. One is called apply. This works with the programmer-defined binary int op, the one we saw before. So the first argument to this method is a binary int op, in this case called bio, and the functional method is compute. So we use bio to call compute on the two arguments. So we could do an addition, subtraction, multiplication, division, whatever, by using the higher order function. I also have apply because for the bifunction and the binary operator, the so-called functional method is named apply. Here we pass as an argument one of these bifunctions along with the two arguments, and then we call apply on the function's reference, in this case func, and we pass in the two arguments. So I'm going to illustrate both direct calls and, you might say, indirect calls by using apply. Let's now turn to the demo. So here's the original example we've seen. We declare a binary int op called div. That's the object reference, and we set it to a very simple lambda. Takes two arguments. Again, the compiler will figure out the data types, very convenient. Then we call compute directly using the object reference, and then we call it indirectly, if you like, by passing it to a higher order function, in this case apply, which then calls the function on the two arguments. Now let's jump to the built-in examples, and as you'll see, the structure is essentially the same. So I've got a bifunction. In this case, to keep it simple, the three data types are all the same. So the first integer is the first argument, second integer, second argument, and third integer is the return value. So what I do here is the same example as before. I've got a simple lambda to do a division. I use that object reference div bf directly by invoking apply, because apply is the so-called functional method, and then indirectly by calling the higher order function and passing div bf as the first argument. Let's now look at the binary operator variation. So as you're going to see, it's simpler, and in this case, it's more appropriate because up here for the bifunction, all the data types are the same, so I don't need that much typing. I can get away with this. Binary operator, single data type integer, that's the type of the two arguments and of the return value. Slightly different lambda, we're going to do an addition this time instead of a division. And then here's the direct call. We use the object reference. We call apply, the functional method. And here we call the higher order function, sending the object reference as the first argument. Now notice for this apply, we can send it either a binary operator or a bifunction. So let's go back and take a quick look at that. The declaration of the parameter is for a bifunction, but a bioperator counts as a bifunction. It's simply a specialization of a bifunction. Finally, for proof of concept, the last example uses a bifunction to take two integer arguments and return an array of strings. So the integer arguments are basically indexes into the arrays that we saw earlier. They're basically English and German words for numbers. And the object reference is called a join. I couldn't come up with a better name. Those are the two indexes, I1 and I2, and we create a string array. And from the first array, we take the item indexed by I1, and in the second array, we take the item indexed by I2, and they're both strings. And then what we do is call apply, so that works perfectly fine. And then for good measure, I'm using the arrays stream convenience function, so arrays stream result. In many examples, by the way, we'd convert an array to a list and then just call the stream with no arguments, but arrays stream is very convenient, does the same thing, and then for each of them, print them out. So the output you can see down below, the division, the high-level division, the division again, high-level again, addition, high-level. The high-level, of course, is always the calling either apply or apply. And then here's the output from the last example. So you can see that the bifunction and the binary operator built in, very convenient. It's a good idea, by the way, to use these whenever possible. You get the aid from the compiler if you should have some data type mismatch and the like. And it also makes the code easier to read in the long run. In summary, you can always roll your own binary int op, or if appropriate, and if you look at that list of 40-some pre-built functional interfaces, you're likely to find something appropriate. You can use the built-in functional interface types. This lesson focuses on two particularly important interface types, supplier and consumer. As you can see, they're both in the package java.util.function, and we're looking at the working file supplierconsumer.java. I've already compiled it. Later on, I'll do a sample run. Let me begin by talking about why these two interfaces are so important. They can be used, by the way, either separately or together, and when used together, they represent, in effect, Java's support for the producer-consumer programming model. This is a programming model that is familiar across the programming landscape. For example, if I use Twitter to send out a tweet, I'm producing a tweet, and I hope, of course, that there are many consumers of that tweet. So Twitter is an app that quite obviously follows the producer-consumer programming model. In Java, these interfaces work very nicely in implementing such a model. But again, you can use these separately, and there are occasions to do so. There's a further reason that these are so important. In the Java doc for the Stream API and the Functional Programming API, you're going to see supplier with a lowercase s and consumer with a lowercase c used quite frequently to describe things. So for example, if I were to write my own collector, in other words, I didn't want to use one of the built-in collectors, I wanted to roll my own, one of the things I would have to do would be to implement a supplier. The supplier interface, you might say, formalizes or standardizes the notion of a supplier, and the same with consumer. Now, both of these are generic. I indicate that below in the documentation, so you can supply any type you would like. You're not constrained, and you can consume any type that you like. A supplier at the syntax level is going to take no arguments and supply a value, and a consumer is going to take, at the syntax level, a single argument and return nothing, void, in other words. So let's get down to the demo part. So I have a supplier. In this case, it's going to supply a list of integers. I could supply a single integer, a list of integers. I can get as rich as I want to. So I have complete flexibility. I call this data supplier. It's a method reference, as you can see down here. Here's rand data supplier. So rand data supplier is going to send back, as you can see, a list, and the list is going to consist of integers. So I just randomly generate some numbers and basically send them back as a list. The consumer is implemented as a very simple lambda. So as you can see, the consumer is going to take an n, Of course, the compiler is going to determine that that's going to be an integer, and then it's going to multiply that by 3 just to do some sample transformation and stringify it by appending a blank. I'm going to print them all out on the same line. I also have a higher order function called doPipe. It takes two things. The first is a interface reference, in this case data supplier, and the next is a consumer interface. This is the data consumer, and basically the doPipe is going to link them together in the obvious way. So we jump down here to doPipe, supplier get. So get is the so-called functional method declared in the supplier interface. So the supplier is going to get a list of integers, and then the iteration over that list is going to be provided by the now familiar for each method. And the for each method is going to pass each of those integers on to the consumer. The consumer is going to do its thing and do a very simple printout. So as you can see, it doesn't get much simpler than this. This is the producer-consumer programming model illustrated in a very, very simple app. Let me jump to the command line just to run this proof of concept. So there's supplier consumer. It will be in the working files, of course, and I'm printing them all out on the command line. You can tell in effect that it's working because the random values generated are all 2 digits, and as you can see here, most of the numbers are 3 digits, and that results from the times 3. This is our first, not our last look at supplier consumer. We're going to do another example that's a bit more realistic, but this gets the syntax out on the table and the motivation for these two very important interfaces. This lesson continues our focus on the supplier and consumer functional interfaces, but this time the emphasis is not so much on the syntax, but on the use. The example, called messagex.java, we're looking at in my Emacs editor, and this is included, of course, in the working files. So let's go over it before I run it from the command line. So in this example, the supplier of a message is going to be a constructor reference. In other words, we're going to use a constructor in effect as a message factory, a very common practice in functional programming in Java. And the consumer of the message is not going to do a lot. It's going to do a little bit of logic, just as proof of concept. It's going to check the message to see whether it's been acknowledged in going from the ultimate sender to the ultimate receiver. In other words, from the supplier to the consumer. So in terms of a simple picture, we have a message stream. There's a mapper which takes a message and may acknowledge it or may not. I make this random just so we have a little bit of logic in the middle so that the consumer has something to do. So in effect, acknowledgement is a coin flip, and the consumer is going to check which way that coin flip went. So let's get to the data structures. Here's class message, pretty simple. I'm going to use an atomic integer to generate IDs so we can readily identify the messages. There's a random number generator. We'll see that in use momentarily. The constructor sets the ID for the message. It also sets the time sent in nanoseconds. That's to ensure that we get different sent times for the messages. If we just use the regular Java time, the granularity would not be sufficient. All of the messages would appear to be sent at exactly the same time. There are 3 very simple read properties: get the ID, get the time that it was sent, and get whether the message was acknowledged. In terms of acknowledgement, there is mark acknowledged if, and the if is really a coin flip. So that's what the random number generator is used for. We basically flip a coin, and in one case we set acknowledged to true, otherwise we leave it alone as false. Notice that this method happens to return a message, and that's because we're going to use this as the argument to the higher order function map. So map is going to take a message, map it to a message, and along the way perhaps change one of the message's properties. Dump and toString are just for printing purposes. So let's move down to the heart of the example. First, what I'd like to do is just show you once again how a supplier works. So I'm now going to use, as noted, a constructor reference as a supplier. So you see the line here in test basics. Message maker is going to supply message instances, and the easiest way to do that is to create a message factory, and this is the new way that you can do that. So it's simply class name, which of course is also constructor name, :new. The functional method, as we're going to see, is get. We saw that before. It's going to remain that. So down here for proof, what we do is use the message maker to get a message, check whether that's an instance of a message. It is. Do it once again for good measure. Check again whether we're getting a message. We do, and so on. So that's the basics. The difference now is that our supplier is just a supplier of messages. Back up here now, we need a consumer. So the consumer of messages is simply going to take a message. So it's a very simple lambda, and in the body, check whether the message was acknowledged, and if the message was acknowledged, do a dump. Otherwise, do nothing. Get messages from source we'll look at momentarily, but this returns a stream. That stream is mapped, so we transform the messages by acknowledging them if the coin flip goes the right way. So the argument to map is a method reference. It's the easiest thing to do in this case. And then we do the for each using the consumer as the argument to for each. So once again, we have map higher order function for each higher order function. Now let's jump down to generate messages from source. So once again, I create a message maker. That's the reference, and it refers to a constructor. So you can see, well, constructor reference technically, message new. An array of messages is created simply by repeatedly calling get on the message maker. So as many as we need, that's how many we get. In this case, I'm generating 15. And then once again, using the very convenient arrays utility class, it's got the stream method. It takes an array and generates a stream. So what we get back from get messages from source is a stream of messages. We can now jump then to our pipeline. Get messages from source gives us this stream of messages. Each message is going to be mapped to mark acknowledged if. Depending on the coin flip, this may change a property or not. And then each of these is going to be sent to the consumer, and the consumer for the acknowledged messages is going to print those out. Let's jump then to the command line to run this, just to be sure. So I've compiled it already. I'm ready to run. So I run it and we get 1, 2, 3, 4, 5, 6, 7, 8. The first time through, run it again. This time we get 5, run it yet again. This time we get 4, and so forth. So we're going to get a random number of acknowledged messages. Again, in the outputs, you have the brace, then the message ID, then the time sent in nanoseconds, and then true, meaning that the message was acknowledged. So we shouldn't see any falses there, or we have some problem with the underlying code. So this example is more in the spirit of how you might use a supplier and a consumer. And just for good measure, we've got a little map in there, the middle, to do some application logic. This lesson takes a look at functional composition. As the name suggests, you can define functions and then combine them in different ways. We've seen this a little bit with predicate already because we've seen both predicate and we've seen predicate negate. In effect, these are ways of combining predicates together. We're now going to take a more general look at how this can be done with the various functional interfaces available in java.lang.function. So let me present an overview. I'm not going to use the jargon you're going to see in the documentation. In the documentation, they like to talk about the before and after function. I'm just going to use pictures to avoid confusion, very simple depictions, and talk about the functions. So we're going to have two functions, doubled is 1. It does just what you would expect. It multiplies its argument by 2, and squared does what you'd expect. It multiplies its argument by itself. So those are the two function references. And now we can combine them in arbitrary ways, but the two basic ways are shown here. The first is this. We take doubled and then compose squared. So the tricky thing, of course, is what executes in what order. By the way, after the compose squared, of course, then we apply. So we're using 5 as the argument. So the question is what happens? And what happens is this. Squared executes first. So the argument to compose is going to go first. So we're going to get, of course, 5 times 5, 25, doubled, 50. So the argument to compose goes first, then the doubled executes. The other way of composing is to do doubled and then. This, I think, is very intuitive. So doubled goes first. So we take 5, double it to 10, and then we square it. So we get 100. Now, compose and then can be applied in arbitrarily long chains. This can get to be a little confusing, of course. You've got to be very careful about what you mean to do when you create these compositions, but the idea is fairly straightforward and it's fairly easy to do. Either case, compose or and then, the name that you're going to find used in the Java doc is functional composition, and there are plenty of examples available. So we're in the Emacs editor as usual. We're looking at compose.java. I'm using only integer data types in these examples, but any data type would do. So you can compose functions of any sort. And I'm also using the very generic type function because we haven't seen that yet. I'd like to get it out on the table. For all of the examples I'm doing, 1, 2, and 3, I could instead use unary operator because the argument type and the return type are exactly the same. But function works just fine as well. So there you see doubled, defined with a lambda. It's hard to imagine doing this any other way now once you get into this functional style. Tripled, and then, of course, squared. So 3 of them, just for good measure, and doubled, tripled, and squared are executed, and you get the expected results. Now we're going to do the composition, first using compose, and then using and then. So with compose, doubled, compose, squared, apply. So in words, that would be doubled the squared value. Triple compose doubled would mean triple the doubled value. And then with the and thens, what we're doing is doubling and then squaring. And in the second example, we're squaring and then tripling. So you can see what the expected outputs are to the right. Print is very simple. It just prints a message together with the generated value. So let's jump to the command line and run this. And you'll see that this confirms the behavior advertised in the documentation. Let me go back then to the Emacs editor. This is a very simple example, really straightforward, because functional composition is really quite nice, quite convenient. I like to keep the compositions short and sweet. In other words, my idea would be to build up a composed function, maybe give it a name, an object reference in effect, and then use that if I'm going to do further compositions. But the basics are here. Compose and then are the tools that you use to build up these very nice and arbitrarily complicated compositions. This lesson is a wrap-up of our recent examples that have used functional interfaces. We're looking in my Emacs editor at the working file functional ifaces wrapup.txt. It goes over all of the points, summarizes all of the points that I'd like to cover in this lesson, but I'm not going to take the points in strict order. So let me start with the obvious question. What do you use functional interfaces for? What is their purpose? Basically, they're used in 3 ways. First, you could have a standalone reference to a function, typically a lambda, and we saw that in the very first code example we used. So there was the binary int op interface, programmer defined. We rolled our own, and it referred to an implementation of compute, in fact, to 4 implementations. So we had add, subtract, multiply, and divide, basically, all implemented as functions that take 2 int arguments and return an int. Notice, by the way, that a functional interface can take, a programmer-defined one in particular, can take primitive types, not just class types. More recently, we've moved on to java.util.function interfaces, that is, built-in ones, but these have the same purposes. They can be used to refer, again, to standalone functions, again, typically lambdas. They can be used to refer to arguments in higher order functions. We've seen that in particular with predicate. And they also can be used as return types from functions, and we saw that with predicate as well. Predicate was returned from a method. So these types have then 3 standard uses. What I'd like to focus on here is the tutorial nature of these interfaces. Let me explain what I mean. If you look at this list, so predicate we saw in the customer example, supplier and consumer we've seen in a couple examples, including message. Function we've seen in the compose example, and I've thrown bifunction into the list because it's the most complicated of the ones among all those 40s, and it's pretty simple. A bifunction takes 2 arguments, t and u are the generic types here, and those types can be different. They could be the same or different, doesn't matter. And a bifunction has a return type r, which also could differ from either of the parameter types. So it doesn't get more complicated than this among the functional interfaces in java.util.function, which is a recommendation in effect about how we should implement these functions, in particular lambdas. They should be short and sweet. They might take a couple of arguments, return a value. They might take no arguments and return a value. For example, a supplier is going to do that. It's going to take no arguments but return a value. A consumer, in effect, is going to take an argument but not return anything. So the possibilities are rich, but the implementations are all quite simple. And that's by design. That's really as it should be. My own sense from using these interfaces is that this package pretty much presents everything that I find that I need. The example, the very first example of the binary int op was in there only so that we could avoid going into the package right at the start. That seemed a little bit too complicated. But in actual practice, I don't find much need to roll my own. But if you do need to roll your own, the rules are about as simple as they can be. So you need an interface. Any name will do. Of course, you don't want a name that conflicts with something built in. And then you need to declare a single abstract method. And in the very first example, that method happened to be named compute. So it took the 2 ints and returned an int. You can mark this with the functional interface annotation if you like, but that's not even a requirement. So all in all, both the built-in examples that we've seen and the programmer-defined interface, in all cases, the functional implementations were short and sweet. In summary, these functional interface types can be used to refer to methods, but more commonly, they're used to refer to lambdas because lambdas are the short and sweet way of writing functions now. This lesson focuses on a question that's gotten a lot of attention in the blogosphere. So the question you see at the top of the working file is lambdas closures.txt. We'll get to what a closure is momentarily, but the question basically is, does Java now have closures? Or, to be more exact, is a Java lambda a closure? If you Google Java, lambdas, and closures, you're going to find all sorts of differing opinions on the question. So let me suggest a working answer, and then we'll get into some details. And that answer is this: a Java lambda is a closure, but. So there are qualifications because closures in Java are not exactly the same, or may not be exactly the same, as closures in other languages. So we want to get into both the differences and why there are those differences. So Java has what might be called closures under restrictions, and there's a very, very good reason for those restrictions. So let me begin with an example, and I'm going to give a working definition. This is a standard one. So a closure is a lambda that closes over. That's where the name comes from, or captures, somehow caches a value from the lambda's own environment. Now that's a little bit tricky. So as a working model, let's go back to Lisp, where closures are used all over the place. And we can look at a fairly simple example. The syntax shouldn't get in the way. And then we can contrast this with what you can do in Java. So once again, I'm using CLisp, which is available. It's from GNU. It's available on all platforms. It's a common Lisp implementation. So I'm in my Lisp environment and I do def var auto counter nil. All I'm doing basically is, in Java terms, declaring a variable and setting it to a default value. So nil in this context is roughly speaking null. So I'm going to redefine auto counter momentarily. Now, comments in Lisp begin with a couple of semicolons, as you can see here. So at the same level as that def var, I have a let. So this is known as a lexical scope, a little tricky. And the idea is this: I have an identifier n, so in Java terms that would be a variable, and I have a value 0, and the value 0 is bound to that identifier end. Now, the scope of that binding is the let itself. So the let starts on this line and it ends with the final right paren on this line. So the lexical scope basically means in this context, you can see n inside the let, but not outside of it. In Java terms, n would be a variable local to a function or to a block within a function. For example, a while loop within a method, that sort of thing. All right, now to the details. Now to setting up the closure. So we do set q. This basically is going to initialize auto counter to something else, set it to something else, and it's going to be set to this lambda. The lambda takes no arguments, notice, but it does reference that n. So it takes n and increments n by 1. Set q is basically assignment. So auto counter is the lambda now, and the body of the lambda increments n by 1. So now we put this to use. I'm still in my Lisp environment. I do a function call on auto counter. So auto counter is a reference to a lambda, effectively. I get back a 1. I do it again. I get back a 2. I do it again. I get back a 3, and so forth. So somehow this n up here has been captured, hence the notion of closing over, has been captured within the lambda, and it is now held within the lambda. At the implementation level, you have something like this. This is basically a depiction of how Lisp does this. Auto counter may seem to refer only to a lambda, but it really refers to two things. It refers to the lambda down here, so there's the code, but it also refers to an n. So that's the closed over n or captured n. And of course, what the lambda does, repeatedly, every time you call auto counter, what it does is updates n. So the auto counter, if you like, has its own copy of n, which came from its environment, and it now can manipulate. Mutate is the term that's commonly used. It can now mutate n. It can increment it in particular. Now, a point to keep in mind is this. Lisp is a language that originates in the late 1950s, the Stone Age of computing. And it was developed in an environment where multi-threading was not in the forefront of anybody's mind. Java closures, by contrast, were developed, lambdas, in other words, in Java, were developed in an environment where multi-threading is foremost in everybody's mind, and threading issues are foremost in everybody's mind. So this motivates directly why Java has implemented closures the way it has. So the basic idea is this: a lambda in Java can pick up lexically scoped variables. In other words, it can basically access values, local variables, in its environment. And we'll see an example of that. I just want to focus on the idea right now. But the thing that a lambda in Java cannot do is mutate the closed over variables. So for example, in Java, the auto counter would not be able to increment n. That's the short version. Now, the reason for that is that Java developers, the people who implemented the Lambdas and so forth, are worried about race conditions and multi-threading. Suppose you had a Lambda that could do this. In other words, that could basically mutate this value n, and you're in a multi-threaded environment where multiple threads of execution are doing the auto counter thing. In other words, trying to increment n. You now have a race condition. You need somehow to synchronize access to n. Things become overly tricky. So the Java way out is basically to say, no, you can close over these values from your immediate environment, in other words, local variables in effect, but you cannot change them. In other words, in Java terms, those variables are treated as final. They're read-only. Now, there's another side to this. The other thing that Java is really trying to do is to encourage us when we write lambdas to write so-called pure functions. These are more commonly referred to as stateless functions in the Java world because a pure function or a stateless function generates its value exclusively through its parameters, the arguments passed to it. In other words, it doesn't have any side effects. It doesn't touch any fields. It doesn't change anything outside of its own local environment, which consists, of course, of its own local variables, if any, and the arguments passed into it. So Java is trying to encourage us to write lambdas as pure or stateless functions because stateful functions may be thread unsafe. And in a multi-threaded environment, we don't want to have to worry about race conditions involving lambdas. In summary then, Java most certainly does have closures, but they are restricted closures, and what we're going to see in the next lesson is a code example that brings that to the fore. This lesson focuses on Java lambdas as closures, and it uses a code example to do so. In the previous lesson, we looked at closures in Lisp, and closures in Lisp are allowed to mutate, that's the term that's typically used, are allowed to mutate the so-called closed over value. We're now going to see that this can't happen in Java, and to illustrate, we're looking in my Emacs editor at autocounter.java. So this is included among the working files, and I've done a homegrown interface for emphasis. I want to call this the counter iFace, and I want to use the abstract method count. We're going to do an implementation in effect of count using lambdas. So let me jump down to the code. I have some documentation up above, in particular an error that you're going to receive if you do something that we'll get to momentarily. So let's first try to do the Lisp thing. So I have int n equals 0. This would count as a lexically scoped variable. So it's a local variable inside demo. Its scope is from this point till where demo closes, and that of course is that right brace. So it's visible basically in the body of demo. Now what I tried to do in this commented outline, because if you take away the comments and you try to compile, you're going to get the error message shown above. So in my first attempt, what I do is declare autoCounter to be a reference of type counter interface. So it's got the count method, but I'm never going to get there. The compiler is going to see right away that what I'm trying to do is not only capture n, that would be okay in principle, but I'm trying to increment it. In other words, mutate it. So that's not going to work. The second attempt, autocounter2, will get by the compiler because what I'm now changing is not a lexically scoped variable, but a field. And that field, of course, is right up there, int k0. K is not declared to be final, so it's perfectly okay in general, and including inside a lambda, to increment, decrement, or otherwise change k. So this is okay. This will work, but it is no longer thread safe. So if you have multiple threads trying to execute autoCounter, in other words, the function that autoCounter points to, this little lambda right here, you're going to have thread safety issues. So you're going to have a race condition. And the whole point, of course, is to avoid those sort of conditions. Finally, let me do this. I now have a int k, but it's declared final. So in effect, k is a constant, 11. I can now do counter 3 equals k times k, perfectly fine. I'm using k, I've captured k, so this is indeed a closure. So k is captured, closed over within the lambda, and I'm not changing it, I'm just multiplying k by itself, so that's perfectly fine. And when I run this and do the system out print line thing, I'm going to get the expected value of 121. Technically, counter 3 refers to a closure in Java with the restriction that the closed over variable has to be final. Now, you're going to read in the Java documentation that this has to be either final or effectively final, which means treated as read-only. But in this context, I need the final to get by the compiler. Finally, let's talk about the way you would do an auto counter in Java. There's no need to do this through a Lambda. We already have a perfectly thread-safe and easy way to do it, and that's illustrated down here. Auto counter 4 refers to an atomic integer. Again, that's in the java.util.concurrent.atomic package. All of the synchronization is built into the data type itself. I don't have to worry about it at all as a programmer. So I just create a reference of that type, and then I can use it to increment and I get the expected values 1, 2, 3, and so forth. So this has been used in various examples we've seen, and for good reason. So Java does not have, in summary, Lisp-type closures. In other words, closures that can mutate the closed over value, but it certainly does have closures. The important point is that a closure may not be the best way to do something in Java because there are better ways of doing it. And this is a perfect example. If you need an auto counter, you can certainly get one in Java. It's straightforward and easy. You don't need a Lambda to do so. This lesson looks at how lambdas can be used to support a programming technique called currying, C-U-R-R-Y-I-N-G. Before describing what this technique is, let me say a little bit about where it gets its name. There's an American logician named Haskell Curry who has two things named after him. Currying is one of them, the programming technique that cuts across programming languages. And the other is Haskell, which is a powerful functional programming language. You could make the case, I think, that the two dominant functional programming languages are Lisp and Haskell. So back to currying. The idea behind currying is fairly straightforward. The idea is to reduce the number of arguments passed to a function. When you reduce the number of arguments, of course, you simplify the call. And in simplifying the call, you reduce the likelihood of errors and so on. It's a simple sort of move, but it can be very, very useful in programming. So let me clarify a bit further in pseudocode. So suppose we have a function called mult for multiply, takes two arguments, returns their product. So we call mult35, we get back 15 as expected. What we're now going to do is produce a curried version of mult. So we call curry mult n5, and the idea here is that we're going to bake the 5 into the curried mult function. So now when we call curried mult, we give one argument, 10. That's multiplied by 5. We get back the product in effect of 10 and 5. So we go from a 2-argument mult to a 1-argument mult. Now, let me jump down all the way to the bottom to make this point. We're going to be doing contrived examples. In other words, I'm going to be working with numbers such as 5 and 10, and there's no particular reason that you would want to bake 5 into a function. But if you were working, for example, in science or engineering, you might be calling lots of functions that use pi or e or similar constants, and it would be useful to bake those into a function so that you wouldn't, for example, confuse the pi and the e versions. So currying, the motivation behind it really is to simplify function calls, reduce errors, and make reasoning about function calls in general easier to do. Now let me get to the Java syntax to explain what we're going to do. We've not seen anything like this before. The syntax is still very simple, but the result is very powerful. So what we're going to do is this. We're going to have a lambda that basically feeds an argument into the body, and this body is itself a lambda. So you can have a lambda that contains a lambda, and that's basically what we have here. In Java, by the way, all of these parens are not necessary. I have them in there basically for readability. So in particular, that paren, which matches that paren, those two could be taken out. Now, I think this is best described by jumping into the programming details. I've got a little more information up there in the documentation, some background, but let me cut to the quick. I'm going to be using, once again, these built-in functional interfaces, and here's the general idea. So you can see at this line we have int binary operator, takes two ints, returns an int, pretty much what you'd expect. We're going to curry that into a unary operator. So we're going to drop one of the arguments. The unary operator takes one int and returns an int. And we're going to do that by using the int function. The int function is really powerful. It takes a single int argument, but it can return anything. And in this case, we're going to return a lambda. We've done a little bit of returning lambdas from functions before, but now we're going to return something that's a bit more sophisticated, something that looks like this. In other words, a lambda whose body is itself a lambda. And as you might expect, you can take this to any level of complication that you like. So the lambda, simple though it is a really powerful programming construct. So let's start with the int binary operator. So I call this mult2 to emphasize that we have two arguments. And you can see the lambda on the right, n1, n2, and the return value is their product, n1 times n2. No big deal. So if we do 10 and 20, we get back 200. You can see, by the way, that the functional method for the int binary operator is apply as int. We give two arguments, we get back an int. Now this is where the power comes in. We have something called curried mult producer, and as you can see, this is going to be a reference. It's going to return an int function parameterized as an int unary operator. So basically we're getting back an int unary operator, takes one argument, an int, returns a value that's an int. And the value is just what we have seen before. N1 is, I'm going to call this the outer argument. N1 comes into this nested lambda. N2 is the inner argument. And the body then of the inner lambda is mult2, apply as int, N1 and N2. So outer and inner. Now we're going to call curried mult producer, that's our reference, with 10. And as you can see, the functional method is now apply as opposed to apply as int. And we get back this curried mult. And this curried mult, again, is an int unary operator. So now I can call curried mult, apply as int 20. So packed away in there, of course, you might say baked into the curried mult is 10. So the product is 200. If I give it 80, the product, of course, is going to be 800. If I now do it again to get another curried mult, if I apply 2,000 as the baked-in value, I then call it with 10, I'm going to get 20,000. If I call it with 3,000, I'm going to get a much bigger number. I'm going to get 6 million. You can see the power of this even in these simple examples. What I like about lambdas in Java is they've kept the syntax about as simple as you could make it, very conventional type of syntax really for a lambda, and they've put no restrictions on the level of nesting you can do, which means on the amount of power that you can get in a very short and sweet lambda expression. In this lesson, we're going to take a step back from the code examples to focus on programming style and how it changes starting with Java 8. First though, a cautionary note. Java remains a class-based, object-oriented language. To put it in different terms, Java 8 adds lots of new things. The most dramatic are the Lambda and the Stream API, but Java 8 doesn't throw anything out. So all of the old constructs in Java remain in Java, and a programmer could program starting in Java 8 and beyond in the same way that the programmer programmed before Java 8. Nothing's been broken, and that's really good news. We've seen the new functional programming constructs. Again, the Lambda certainly is the new dramatic entry. We've not seen anything quite like this before in Java. And method and constructor references are also, I think, inspired. They're very simple. They make methods easy to plug into pipelines. They make it easy to use constructors as factories. So hats off to all of those who helped to design and implement these new features. We've also seen that the Stream API, with its reliance on higher order functions such as filter and map, invites the use of this new functional style. What's easier than dropping in, for example, a lambda into a filter or map as an argument? And these functions require functions as arguments. That's what makes them, of course, higher order. Now, the thing to keep in mind, I think, is that there's still a place for very traditional Java in what might be called the imperative style. That's what it's usually described as. In other words, you write a method or a constructor, you have a statement, another statement, another statement. You could be assigning values to fields, doing tests, looping, whatever is required. So this traditional imperative style is still legitimate. There's no reason for us to throw it out. In fact, the biggest challenge for a programmer, I think, starting with Java 8, is going to be developing a sense of when to use the new stuff and when to stick with the old stuff. This is an experiment. It's going to take some time. I find myself, for example, at certain times using new style and then thinking, well, really, there's no point in doing new style. I ought to just do this old style. It's easier and cleaner. So finding that right balance is going to take some time and practice, but it's certainly worth doing. I think there's no doubt about that. I can't imagine a cleaner construct than the Java Lambda. It's really, really well done, and it deserves, I think, to be in first place among the new constructs. Now let me talk a little bit about multi-threading in particular, because multi-threading remains in Java. With Java 8, before Java 8, after Java 8, presumably, it's going to be the way to support concurrency and parallelism. In other words, the way to take advantage of these new multi-core machines that we're all using. And functional programming fits in very well here because they've done a super job of trying to encourage multi-threading while making multi-threading safe. So lambdas in particular are designed to encourage pure or so-called stateless functions. In other words, functions that don't have side effects, functions that work only with the arguments passed into them, generate a value, and send that value, for example, further down a pipeline. Pure functions are thread-safe functions. So avoiding race conditions is encouraged, I think, by the use of lambdas because lambdas encourage you to write pure functions, very simple functions, side effect free. Not every function can be side effect free. We know that. In my own programming, I try to confine the side effects to methods because I understand that better. I'm more used to doing that. And I try to make the lambdas pure functions, period, and move on. Now, the Stream API that includes parallel and parallel stream makes doing multi-threading absolutely wonderful because basically you delegate the management of that to the runtime system. You don't have to worry about an executor service. You don't really need to know a lot about the underlying fork join pool or anything like that. When you invoke parallel and parallel stream, what you do is you get multi-threading, you might say, almost for free. Now, there are still thread safety issues, no question about that, but Java helps you to deal with that because collectors in general, unless you're doing something very funky, collectors in general are thread safe. The built-in collectors certainly are. A couple of other points. There's been lots of benchmarking done. I've followed this fairly closely in the blogosphere, and the consensus seems to be that there's no serious performance penalty in going functional in Java. In other words, using the new Stream API, plugging in Lambdas, using method references and constructor references where appropriate does not come at a high performance cost. It seems to be basically a wash. And I think what we can expect from Java, as always, is as we get new releases, the implementations of these things are going to be refined and improved. So in general, I try to follow this cliche. Where functional makes sense to me, I use it. Where it doesn't, I don't. That's trivial, of course, to say, but it's very hard to do, and it just takes a fair amount of practice. If you've been using Java, I assume that, like me, you applaud these new additions. You're eager to see where they can be put to good use. And I think the more code you can write using these new constructs, the better, because that will give you a sense of how to enact the compromise between the old style of Java and the new style of Java. In this lesson, we're going to look at a code example that illustrates the difference between the traditional imperative style of doing Java, so we could call that pre-Java 8 style, and the new functional style. We're in my Emacs editor looking at the source code imperfunc.java, but let me jump to the command line to run the application, and I can use the run to provide some information. So I've compiled already, I'm ready to go, and I hit return. So let me explain what's going on in the background. The program generates 50,000 random numbers. The range is between 0 and 9,999. And then it filters out, as you can see here, both powers of 2 and prime numbers among those numbers. So you can see, for example, that most of the powers of 2 are captured. However, some go missing. For example, 2 is not in that list. But just eyeballing it, it looks like the others are. And then the list of primes goes on and on and on and on. So we'll fast forward through that till we get sort of to the bottom. And then you can eyeball to confirm. All of these numbers had better be primes. Otherwise, I've got some flaw in my logic. And there you can see the end of the primes starting at the top, 61 down to 2. Now the program does this twice, once in a imperative or traditional style of Java programming, and then again in the functional style. We're not interested so much in the algorithms, we're not interested so much in the flow of control, that sort of thing. We're really interested in the style. So let me jump back into Emacs, where we can look at the source code and get a sense of that style contrast. So let me start with this class. I've got some documentation up above. So this is an integer candidate. So basically the 50,000 values that are generated are then instantiated as int candidates. So an int candidate has a type that's of interest to us. It's a prime, it's a power of 2, or it's neither. It's got a type and a value. So what the constructor does basically is to generate an int value, wrap it up as one of these int candidates, and then set the type to whatever happens to be appropriate. So there's some logic down here to do that. There's also a get type and a get value in order to read those properties. In the main class, I've got some utilities. So this is power of 2. It's a little bit mysterious. I provide some documentation, but it works and it does so efficiently. Is prime, as noted here, is a bit clunky, but I think this is the way you would do it in production. So it grabs out the prime numbers from the list. Generate candidates constructs a list of these int candidates. Currently, I'm doing 50,000. And then we're basically going to process these in 2 different styles. So we'll cut down here to demo, and this is the heart of the application. So first I generate a list of candidates, and then I make a copy of it. So I want each style to have its own copy, so each style is free, so to speak, to do with the copy whatever it likes. So we have identical values in both. Now I'm going to move down into the imperative style. First, let's eyeball it to get a sense of how big it is. So it starts basically at this line. So I've got this marked, and then we come down, and it comes down to here. So it's more than a screen full, maybe a screen full and a half, a screen full and a quarter, something like that. That's not necessarily a bad thing, of course. The logic is not deliberately obscured or anything like that. I'm trying to do this in a reasonable way. So let me start here. I create a map. The keys are the types, so we care about primes and powers of 2. And then the values in this implementation are the list of integer values that were generated. To store those, I've got a powers of 2 and a primes list, and those are going to be put into the map. So I now go through an explicit iteration, very traditional sort of Java. For each of the candidates, I grab the type, I grab the value. I then do the filtering in effect. If it's a power of 2, I put it in one list. If it's a prime, I put it in another list, no big deal. I want to sort these in descending order. I want to sort both lists, so I'm constructing a comparator right here, and that's very traditional Java. Then I do the descending sort on the powers of 2 and on the primes. And then finally, I take those lists of numbers, I basically stick them in the map, so now I've got what I want. So I've got a map, the keys are power of 2 and prime, and the values are lists of numbers. And then I go through a for loop in order to print them all out. So I'm doing this in a relatively straightforward, uncomplicated way. Now the functional style is dramatically different. And the biggest difference, as you can see just by eyeballing it, is that we're now talking about whatever, half a screen, 2/3 of a screen, something like that, but it is clearly much shorter. I'm not saying that that alone should recommend it, but this is certainly one of the benefits of this new style. It doesn't take as much code to do the same thing. I've not mimicked the logic in the imperative style exactly. I get the same result in effect, but I do it a little differently, and it would be easy to tweak this to use exactly the same steps, so to speak. So the first thing I do is build a list of integer candidates that's of interest to me. In other words, what I'm going to do is filter out those integer candidates that are neither prime nor powers of 2. Then I'm going to do the sort right here, and I'm going to sort on the values. It doesn't get any better than this in my view. You just drop the lambda in effect, as the comparator, you're done. And then I collect all of these into a list. Again, a very nice feature in the Stream API. I then use that list to build my map. This is a one-liner basically. It's just a stream followed by a collect because of the grouping by, that wonderful, wonderful method in the built-in collectors. And then when I print out, I'm doing pretty much the same thing as above. That is, I go into an old style for loop. I print out the message, but then I just grab from the map each of the values, stream it, get the value. Distinct, by the way, is very, very nice. I'm filtering out duplicates right here. I could have done that elsewhere, but I'm doing it right here. And then just printing out either one. Now let me make a final suggestion. This functional style code is clearly shorter, and I would argue simpler than the corresponding imperative code. Imagine now if we decided to go multi-threaded. The changes here would basically be in two places. We would change this stream up here to a parallel stream, and we would change the stream down here to a parallel stream. For the printing, we'd want to use a serial stream. We want these things still to come out in identifiable order. So basically, there would be two changes, from stream to parallel stream. To do the imperative code would be a bit trickier. First, we'd have to decide on an approach. Probably, I would use the fork join framework. If you're not familiar with that, it's very powerful. You also might use a executor service. You could do it either way. You could also, of course, do it very old style, do the synchronization yourself, but that's a little too tricky. So if you went multi-threaded, the changes here would be, I think you could argue, trivial, but they would not be in the imperative style. Now this example, of course, is not a proof that one style is better than another, but it's an illustration of the obvious benefits that come from the new functional style. And I have to say that I certainly buy into those benefits. I like this new functional style very much, and I certainly hope that you're going to give it a try and that you'll come to like it at least as much as I do. This lesson is the course wrap-up for functional programming in Java. We've been through lots and lots of code examples. We've explored functional programming and the context in which it resides in Java 8. That context, of course, tends to be a data-rich environment in which the Stream API comes in very, very handy. In terms of the big picture, the 2 points that strike me are these: that what you get with Java 8 with the new functional constructs is simply a better and easier way to write apps in a data-rich environment. And of course, we programmers now work regularly in such an environment. We've done that for some time, but now more than ever, we have to deal with large data streams. Typically, we need to do the filtering, the sorting, the reducing, the collecting, all of those things that are made easier with the new functional constructs and the new Streams API. Both, of course, go together. That's no accident. So my hat's off to all of those in the Java community who worked to bring this about. It seems to me that the Lambdas are just inspired. The syntax is as simple as it could be. The semantics are relatively straightforward. As long as you stick with pure functions, stateless functions, including predicates, you're going to be in really good shape, particularly when you have to go multi-threading. There are smaller changes as well. I think the method and constructor references follow exactly the same theme of simplification. They're easy to use. Method references are easy to plug into pipelines, that is, into the Streams API, those wonderful higher order functions such as map and filter. They don't have quite the flexibility, quite the new dramatic appeal of Lambdas, but they're important additions, I think. Also, we've seen that Java 8 brings a lot of stuff in, but it doesn't throw anything out. So at a very pedestrian level, that of course is important. We don't want to have to learn new things because we can't do them the old way. We can still do things the old way. It's just that now there's a better way. For all of us, I think, getting used to this new mix of imperative and functional programming is going to take some practice. It's going to take a while to develop a new style that is comfortable, that has the right mix of the old and the new. But Java has always undergone change, and that's a good thing. And this change is particularly dramatic and welcome, I think, because it simplifies things. That's the most important thing to remember. Things are now easier to do for us programmers. So it's been, for me, a fun course. I like functional programming very much. I hope that enthusiasm came through, and I hope that with practice and over time, that your experience with functional programming will become at least enjoyable as mine has been. So best of luck, and let's move forward and get into some functional programming in Java.